Hello. Testing. Hello. Hello, everyone. Thank you all for making it here today. My name is Alejandro Sevilla. I'm on the leadership team for the MIT Climate and Energy Prize. And it is my absolute pleasure to kick off this event here today. Thank you all. And before we begin, I'd like to take a moment and thank everyone who makes this event possible. This includes our megawatt sponsors, Chevron Technology Ventures, Equinor, Amgen, as well as our kilowatt sponsors, AP Ventures, Rose Rock Bridge, Acario, Temasek, Mitsubishi Heavy Industries, Mitsubishi Corporation Americas, Mint, the MIT Sloan Sustainability Initiative, as well as the MIT Energy Initiative, as well as our partners, especially the Engine, both the Engine Ventures and Engine Accelerator, who have so kindly lent us this space, as well as our friends over at Greentown Labs and some of our partners overseas, especially the TUM Venture Labs. And also our team, who this event and competition would not be possible without. We're all students. We're all doing this in our free time. And we do it for two reasons. First, because we really believe in the mission of CEP, which is to advance the most promising startups that can tackle climate change. And second, because it's a lot of fun. This is a celebration for entrepreneurship, and we hope that you enjoy the event. So we're around here, so if you have any questions, I'm happy to answer. So this is what we have in store with you today. So we'll kick things off with some welcome remarks from Todd Hines, who I'll introduce here in a second. We'll have blocks of pitches, then in between with some coffee breaks, a panel, which includes from people from Clean Energy Ventures and the Engine Ventures team. We'll have some lunch. And then finally, after the last that last batch of startups, the judges are going to go in a separate room and deliberate. And finally, we'll come back here and announce the 5 finalists who make it onto the final, and as well as the winner of the semifinal that's in a debt of a $5,000 check. So with that, I'd like to introduce Todd Hines. He's a senior lecturer at MIT and the advisor and co-founder of CEP.
Old timer here. All right. Well, it's great to be here. It's good to see everybody. And I want to give an extra thanks to the amazing student team that runs the CEP. It's really hard to understand the amount of work that goes into this, and it's great to see how large the team is, because I know how much work it takes. And a good example of that is that we had 70 or 80 judges that already helped get the list of 161 companies down to the team that the groups that we have today. And you got to imagine coordinating that many people and having online, review sessions and pitch sessions, and then also engaging all the strategic partners. It's such a vast amount of work, but it was great to hear the comment around how it's fun too. I think you have to be excited to be in this space and engaging with people from around the world to address really the critical challenge of our generation, of your generation. I also want to give a special thanks to TUM. The semifinals for international teams are next week in Germany. And so it was in London before that and Paris before that. And I want to give another acknowledgement to the students for expanding the competition. The first year we did the competition back in 2008, it was international as well. We had 100 teams from around the world. And it's changed over the years. So, as the markets change, initially we had Eversource as a main sponsor. So we had a big utility that came in and said they put in 100,000. And we had the DOE that put in 100,000 as well. And that's actually what kicked it off. Bill Allett was able to get 200K as for the initial competition. But then he realized there was a lot of stuff to do, and so he called me up. I didn't realize it at the time, but it was a bit of a job interview, because I had helped him launch the Climate and Energy Ventures course in 2007. And that's a class, a graduate course at MIT that brings together engineering, science, business, and policy students from across MIT and Harvard. And the first year I was really just helping kind of get it going, but with the competition, it was clear there was a lot of work that was needed. We had to run the competition from zero to launch in about 4 or 5 months. So imagine with like nothing, there's no book to work with, there's no materials to work with, there's no content. We had to do it all ourselves, and this is before AI, so we had to actually put the work in. And it was a great experience. I had a lot of fun doing it, and I was working full time at Citizens Energy, doing wind development and carbon offset product development, and all sorts of fun stuff. And it was really great to see the competition launch, and it's been really great to see how it's evolved over the years. The funding sources have kind of come and gone, and that's been a real challenge as to adjust to the funding landscape. Um, when we started, there weren't a lot of competitions. It was one of the only clean energy business plan competitions out there. Clean Tech Open had just gotten started as well. So funding was a little easier to get to. And there's obviously a lot of other competitions now, and so there's a lot more noise out there. And it's great to see the teams that we're able to get in here and participate. And we hope we're providing a lot of value. The real goal of the competition when it started was to help, put these competitors up on stage and give them a place to show their stuff and engage with experts and get feedback. And I think we've really tried to help make this a positive experience, whether or not you win the prize. And one of the things that we've done is create a whole set of AI tools. I hope everybody has been able to use Jetpack. Raise your hand if you were able to use Jetpack as part of the process. All right. If you don't know what Jetpack is, I suggest checking it out. Just Google MIT Orbit Jetpack. But it's a tool that really helps people as they're starting companies understand the process and the landscape and really iterate more quickly. We used to take a whole semester for a course at MIT. You can do in about an hour now. And so the question is, what do you do with that extra time, right? You got to engage. It gives you time to engage more customers and hopefully more insight into who the right customers are to engage. Because I think that that's one of the big lessons learned over the years that I've seen is some companies, go too far down the wrong path. And so if you go out and do 100 calls but it's in the wrong direction, it's not going to be best use of time. So hopefully we can use these tools to more effectively guide companies as they're getting started, and even as they scale and operate. So it's definitely an area I'm very passionate about. And one of the things I do want to highlight, we are writing a book called Climate and Energy Ventures. It's based off the course at MIT and the competition, and we're getting lessons learned. We've done dozens and dozens of case studies. So that book is coming out this fall, and hope you can check it out. And hopefully that plus a new set of AI tools. Jetpack is kind of a more general entrepreneurial tool, but the new version of the tools will be very specific on climate and energy, taking into account things like supply chain, regulations, how to get to off-balance sheet financing, capital, long-term capital planning, stuff like that. So this is kind of the mid checkpoint for the competition. There's still a lot of resources that we can help you get access to. So please be proactive at engaging with the MIT community and the broader climate and energy community. If anybody's out there that wants to be a mentor or support the teams or the competition in any way, please reach out. I should highlight that on the funding side, it has gotten challenging. Things are kind of tough these days, but we were able to get enough funding for the budget this year. But we are going to start raising more funding from alums from earlier in the competition, going back 10, 15 years. You got a lot of people that are now successful. So we are creating a place where you can donate, and that money gets stored at MIT in essentially an endowment that will then support the competition more with more consistent cash flow. So the students aren't scrapping for every last penny. At least there's some foundational funding that can keep the competition going, even if funding becomes a challenge. So with that, I want to thanks again for everybody who's here. Thanks to our judges who have come in today. This is a big chunk of time. Hopefully you're getting a great experience out of it, and I think you will. So enjoy the rest of the competition, and make sure to come back here in April when we have the finals. All right. Thanks.
Thank you, Todd. Yeah, so let me introduce the semifinalists. We have a great set of batch here of startups ranging from energy to advanced materials and carbon management. They're split across here from the three like blocks of time, but they'll each have 7 minutes to pitch, followed by 7 minutes of Q&A led by our brilliant judges. We couldn't have asked for a better panel. We have Masanami from Montauk Climate, Rachel Field from the Engine Ventures team, Saif Balani from Foundation Asset Management, and Yusuf Arub from IMCO, and finally Richard Collins from the Engine Ventures team. So with that, I'd like to bring the first startup to stage, Earthflow AI.
Hi, everyone. I'm Alice News. I'm a PhD student at Stanford.
Hi, I'm Isaac Ju. I'm also a PhD student from Stanford.
And we are Earthflow AI. I'm so sorry, guys. Okay. We know that the energy transition is going to need subsurface energy projects to meet net zero by 2050 goals. Earthflow AI is going to make reservoir simulation faster, cheaper, and safer for all subsurface applications using our industry-leading general-purpose AI-based physics simulation. Our prototype is already being used by industry leaders like tech companies Microsoft and NVIDIA, and traditional companies like Shell, Chevron, and ExxonMobil. We know that there's global buy-in from the international community to meet net zero by 2050 goals. Every iteration of roadmaps from the IPCC, the IEA, they all include a massive scale-up of subsurface technologies. Our beachhead is carbon capture and storage, or CCS, and conservative estimates say that's going to need a ramp up of 200 times. Geothermal, 25 times. Lithium brine extraction, 25 times. Geologic hydrogen is an early stage technology, but some roadmaps see it accounting for as much as 5 terawatt hours of underground storage capacity. Our service addressable market just for CCS simulation by 2050 in the US alone is 20 billion. Add the other industries I spoke about, that's another 60 billion. And physics simulation is going to be essential for all of these. Technologies like CCS and geothermal, they're already mature compared to other clean energy alternatives. And lithium brine extraction is going to be essential for supply chain security. We're focusing first on CCS. Some of these roadmaps say we're going to need 5,000 new CO2 storage projects built by 2050. That's a lot. And as seen here, each project needs to go through a very lengthy cycle of planning, permitting, operations, monitoring, and physics simulation is going to be important at every single step. But here's the current bottleneck. Using traditional simulation, it can cost $4 million and 3+ years per project, making it daunting for new players to get involved. Current industry tools, they're developed for oil and gas. They're not developed for CCS. We are designed for CCS, but we're compatible with legacy oil and gas. Other competitors, they use commercial simulators, but what if there was a better way to help new players and accelerate the energy transition? That's where we come in.
Although the challenge is immense, we have the most qualified team to tackle this. We are the pioneers in the AI-based physics simulation for subsurface modeling, with our research being cited over 700 times in just 3 years. And we combine cutting-edge AI expertise with deep domain knowledge of carbon storage, exactly the scale to scale up our industry. And okay, our first prototype for CCS Net is online, available for everyone to use. This web app is powered by our AI-based full physics simulator that is 700,000 times faster than the incumbent solutions. CCSNet revolutionized the subsurface flow modeling through 3 critical dimensions. First, speed. As this images here show the incumbent solution that often takes weeks to finish one scenario, our AI-based solutions deliver results in milliseconds. Such a speed up allows us to do real-time decision-making, which is previously impossible. Second, cost efficiency. Our web app eliminates the complex workflow of subsurface simulation, which makes the project cut the project cost by 95%. And more importantly, the third one, the safety. Our web platform captured the uncertainty through running tens of thousands of possible scenarios within minutes. By doing that, we can have the probabilistic maps of CO2 plume entering different regions, and that will help engineer understand and also mitigate the risk across the entire injection process. Also, I want to talk about what fundamental approach is different from other AI solutions in the space. Most of players are focusing highly specialized target models. We're taking a much more ambitious path. We're building a true general purpose simulator that is trained on massive high quality data that will allows us to take various input like the geo model, well structures, and well configurations, and generating corresponding dynamics of any locations and time at a lightning speed. And also, the biggest company in the world are already using our demo project. Our web demo, like this one shown here, has attracted hundreds of active monthly users. Many of them are from the big company like energy giants Chevron, ExxonMobil, and also tech company who have the energy initiative. And this customer outreaches once again validate our growth strategy. We start with this free app. This creates a powerful funnel, allowing us to get connected with the key player in the space. Those guys can be our first paying customers. And by far, we have late-stage conversations with 3 real carbon storage operators that want to integrate our website into their daily workflow. And the revenue model shows on the right there evolves in 2 phases. First, we start with the 10 bespoke customers, and then we transition to SaaS model when we scale up our model. And that guarantees a very strong unit economics that our gross margin climbing from 73% to 85%.
Currently, the CCS industry is sequestering 50 million tons of CO2 per year. But to meet climate goals, that's going to need to become 5 to 10 billion tons per year by 2050, which means a scale up of 2 orders in magnitude. But CCS is not, it's just the beginning for us. You can apply our recipe to any subsurface flow domain, including geothermal, lithium brine, and also geologic hydrogen storage. We are building a commercial expansion of CCSNet and expanding our technology into new markets. Next slide. Earthflow AI has the expertise, the edge, and a commitment to the energy transition to revolutionize subsurface flow simulation. So invest in us to supercharge the energy transition. Thank you so much.
Thank you so much.
Is this on? Thank you very much for the presentation, super interesting. I had a question about the cost reduction component of your pitch. How would you estimate the impact of your solution on bringing down the cost of carbon sequestration in terms of dollars per ton, and what's the timeline before reaching that point?
That's a great question. And we have a slides that can yes. So for the the cost production reduction that I showed earlier, that is derived from the cost we can bring to the simulation efforts that you're gonna do when you have the storage project. Because traditionally you would spend like $250 per project, because you have to purchase for example, like the incumbent clouds, and also pay for the engineering team that are gonna operate those very complicated simulator. But for our solutions, we incorporate all the upfront training costs. And because our tool is so easy to use and well-trained, well-suited for the project, it will make the cost of every project to 80K. That's like a 95%. So that will help to initiate a lot of projects. For example, for the small to mid-size carbon storage operator who cannot afford like an in-house experts, and they can use our tool. They are willingly to pay for our solutions. And as for the bigger, like the second part of your questions, I believe, how do we achieve that? Again, like there are two stages. If we focus on like we have done a customer segmentation. Okay. For the big energy giants, they have in-house simulation team indeed, but what they care more is how to make their storage project very safe. So they care about the diligence. So our probabilistic approach enabled by this real-time simulation capability will help them to really put that to a different level. And as for the second group, like the mid-size CCS developer, they really want to bring down the cost so that they can carry on their project to make sure the monitoring, the well to continue, like monitor the injection process be safe. So that's kind of how we're going to scale up to achieve that goal.
Thank you.
Thank you so much for the presentation. Super helpful to better understand your solution. I wanted to better understand the business model side of things. So you mentioned having a lot of customers on the beta or using the beta demo. Would love to better understand how you're thinking about the pricing model and whether it would differ by like different types of customers and categories, and how much of it is like a one-time versus like a recurring element.
Yeah, we want to start with more of a bespoke consulting model to get customers more comfortable with us at first, develop a rapport, develop that proprietary training set. And once we feel like we're an accepted player in the field, move to a SaaS model where you can buy our service to whatever degree of compute you need.
Also, I want to like chime in. I think it's very, very important for us to start with this 10 bespoke model, because for subsurface system, the uncertainty is the challenge. So we have to really do this engineering consulting, collect preparatory data, building the artifacts for those different players across different domains. And in the meantime, we have the know-how and scale our fundamental models. Once we to a point now that the model really can be useful, plug and play for a lot of users just to subscribe to our model. And then we will transition to this SaaS kind of platform where we can charge per GPU compute or sign like a, like a deal so that they can use our clouds. But the first 10 customers or the first engineer consulting is very important for us.
Awesome, thank you.
Thanks so much for the presentation. I wanted to double click on the proprietary data sets that you mentioned. So would love to hear more on just sort of where you're at on the data sets that you've already used for the demo, and then sort of how you're thinking about continuing to expand that over multiple generations of this platform, and to what extent that's sort of coming from potential customers or partners versus other sources for those data sets.
Okay. So our academic prototype is built on top of the data generated from this reservoir, industry standard commercial reservoir simulator by Schlumberger. But now we're moving away to our Stanford-led open source multi-physics simulator that is already being used by the storage company for permitting. So the physics embedded in our simulator, the physics-based simulator, is well validated, and also it's very scalable. So now we're integrating our entire training pipeline data collections with our own open source simulator there. So the data, we're gonna be able to commercialize them. And moving into the future, once we have the, like a customers that we're gonna do the project together, we're gonna be able to integrate their user data even more, like the reservoir model and their well log data, seismic data, on the model that we train from these high fidelity simulators. And that's kind of our for data generation.
The proprietary part also comes from our treatment of irregular grids and some of the research we've done at Stanford on how to build a wide training set.
Yes, we're not only focused on just like the simple Cartesian, this is more technical, but we're trying to build a model that will be able to take all kinds of data set. Yes.
Okay, there's only 30 seconds, so I'll ask a very quick question. I guess on this, so I get where you're going from the geological carbon capture storage. How universal is it? I mean, you say geological hydrogen so nascent, like geothermal very different. How universal is this in terms of the model?
We've spoken to the geothermal operators. The training set for CCS isn't one-to-one, but let's say we've done like 95% of the legwork. It's mostly transferable. So when we say general purpose simulator, we mean it.
Yeah, we mean it. We want to focus. Our vision is to build a next generation subsurface modeling simulation tool that will be able to expand not only carbon storage, but also to other subsurface energy processes that share very similar physical governing equations. And I believe we can do that.
Thank you, guys.
Guys, careful about this clicker. You.
So there we go. Next up, Polygon Power. Yeah, it's at forward and back. Is this on or?
Good morning, everyone. At Polygon Power, we've been thinking, if nuclear energy has been around for decades, why is there still a growing unmet demand for clean, reliable power? Well, for starters, traditional projects are just too big. That makes them risky, prone to cost and schedule overruns, and they just take a long time. In short, they're not scalable. Now, small modular reactors were the industry's response. Through modularization and standardization, they are supposed to be more scalable, but due to diseconomies of scale, they face high costs of electricity. In short, they're expensive. Advanced reactors, to varying degrees, aim to target both problems, but they face low technology maturity, which is an issue in an industry that is as slow-moving and risk-averse as nuclear. For example, many of them want to use unqualified materials, i.e. not yet approved by the regulator, and that process has historically taken over 20 years in some cases. And so at Polygon Power, we've designed our reactor specifically to address these questions. For one, it is factory manufactured to ensure scalability. This also de-risks part of the project by moving a significant portion of the work from a construction environment to a highly controlled manufacturing environment. Now, we aim to provide low-cost technology by fighting the diseconomies of scale by providing high-power units, or more specifically, high-power density units. Through our unmatched power density, we can provide the same power, or 4 times the power, as our competitors, besides having similar scale systems. And so by fighting those diseconomies of scale, we can provide low-cost technology or electricity as low as $35 per megawatt hour, despite also being an SMR. Finally, to ensure that our technology is quickly deployable, we use pressurized water reactor technology, which is the most commonly used technology around the world and has been around for decades. This allows us to leverage decades of experience as well as existing regulatory frameworks, ensuring a fast licensing time and fast deployment. And so how do we do it? Well, through targeted innovation. Again, innovation in the nuclear industry is difficult and costly, and so we only really focus on one component, the steam generators. Granted, these components are huge. They're taller than the building we are in, and through our compact heat exchanger technology, we're able to shrink them down to the size of roughly a cubic meter, actually about the size of this podium. This allows us to fit them inside the reactor vessel, and crucially, it also allows us to shrink the containment building, which is the boundary between everything nuclear and everything non-nuclear, from a building size down to component size, something that can be manufactured and transported to the site. So we go from building to component, construction to manufacturing, project to product. Again, we target scalability. There is a tremendous market opportunity for our technology, with the clean energy transition providing a over $1 trillion market, of which small modular reactors like ours are expected to take up $300 billion by 2040. On the environmental side, by being a truly scalable and technologically mature technology, Polygon offers our best shot at actually tripling nuclear capacity by 2050 as pledged, which would save 1.4 gigatons of carbon emissions in the US alone. Now, we aim to capture this opportunity through an OEM business model where we don't supply the entire plant. We supply the nuclear hardware, pre-tested and pre-assembled, fully functional by the time it arrives on site. Now, obviously, this results in initial sales revenue where we can take on part of the project risk by providing our technology at fixed cost contracts rather than cost plus, as is common for construction, which is a major benefit to utilities and drives, to a large extent, their traction with our technology. But that's really only when the party starts, because then there is our long-term aftermarket revenue, as nuclear assets are long-lived. Current reactors go up to 80 years. There are even some whispers for some to go up to a 100-year lifetime. Now, we can expand on the typical, let's say, maintenance-based revenue source by also providing or manufacturing and providing the fuel for our reactors, which is a relatively common practice in the industry today. Now, as for our first set of milestones in reaching this position of being in business are focused around the regulatory aspect, specifically regulatory pre-approval, which is the first step that we aim to have by 2027. Now, to get there, we'll also expand our team. And in the process, we will also further work to formalize much of the traction that we've been seeing in our stakeholder engagement up till now through LOIs and MOUs. We'll also further file IP to further protect our technology. Now, as for where we're at the moment, we are not at square one at all. We are building on 15 years of research here at MIT, both in the reactor concept itself, as well as the compact heat exchanger technology. We have full-scale tests on sections of our heat exchanger. We actually brought part of that heat exchanger. You're welcome to come take a look after the pitch. And we've also filed IP on parts of the technology. On top of that, we've been seeing significant traction both in prizes and competitions like the one today, as well as in our stakeholder outreach. Now, to wrap up, I want to emphasize that we don't just have the right technology, we also have the right team. Our founder, as well as Lucas and myself, we're all nuclear engineers here at MIT. And we also have on the business side strong backing by Doug and Sully, who couldn't make it today. And on the advisory board, we have three superstars. There's Karush Shervan, who's a world-renowned professor in nuclear engineering, focusing specifically on designing cost-effective reactors. Then there's Giorgio Lucatelli, who specializes in mega project management with a keen interest on nuclear projects. And finally, we have Alex Algard, who has founded and led several businesses to success and is also helping set up Polygon for success. So with that, that is the very brief introduction into Polygon Power, and we'll happily take any questions you might have. Just in time.
Thank you very much. Could you begin to just describe the, let's call it the technical roadmap of how you're thinking about it and kind of the key milestones you're trying to hit, and maybe just talk a little bit order of magnitude of cost of how you're thinking about it?
Yeah. Do we have the slide on the?
Yeah, on the roadmap, it should be here. Yeah, there you go.
All right. Yeah. So you can see here the different timelines that we have for the financing. So you can see this is a long-term project. We have the licensing aspect, the manufacturing for our units, and then the commercial development. Our edge for long-term, as Emil explained, is really the economics and really delivering nuclear power plants during the short amount of time. Our short-term and mid-term edge is actually our licensing. We're based on pressurized water reactors. The Nuclear Regulatory Commission has already licensed 7 pressurized water reactors in the past 25 years. So they have experience doing that, unlike many of our competitors. So we are aiming to leverage existing frameworks in order to move as fast as possible on the licensing piece and to secure the different stages of funding before starting to manufacture or really building the first projects.
Maybe if I can quickly add on that, the importance of licensing. If we get our regulatory pre-approval, that means we are the second SMR company to get that. There's only one other NuScale, and all the others have no formal regulatory progress.
I think maybe to build on that question, 100% agreed on the licensing and the regulatory, but actually on the technology itself. I mean, you said you have a unit, right? The size. What's the next step in terms of that? So in terms of the technology that you're going to need to do to de-risk that, in terms of more integration, the experiments, the kind of next step down those lines.
Yeah, I can take that one. So the current stage that we have for our compact heat exchanger is that we're asking questions about reliability. So we proved that we can operate them. Emil mentioned, 15 years of research, and we've been doing that during those 15 years is really trying to test those compact heat exchangers under nuclear operating conditions, so high temperature, high pressure, irradiation conditions. And now we want to de-risk reliability issues. So instead, the questions that we are trying to answer now is, are these going to operate for 10 years, 15 years, or 20 years? From the economic point of view, it doesn't really change the case, but we want to see, depending on how much testing the NRC will ask us, and really based on that, that's how we think we will spend the money on the R&D. So one next step, just to give you an example, crud issues. These are really tiny tubes where the heat exchange will occur, and so we have a risk of accumulation of particles, and so we want to test a new type of material making these heat exchangers in order to mitigate the risk of crud, which is this accumulation of particles.
Yeah, thank you so much for the presentation. I had a quick question on the cost target, the $35 per megawatt hour that you quoted. I guess that is like the aspirational target. And if so, could you walk me through the process of getting to that number?
Yeah, so we have extensive models. We're using a tool called TIMCAT developed at MIT. It is based on over 800 system structures and components that go into the nuclear power plant. So that's our costing. And then we have the financing aspect. The fact that we are a small reactor compared to large reactors, we lose in terms of economies of scale, but we have a lot of financial flexibility. And so we have a financial model that is linked to the costing model that we have in order to code those $35 per megawatt hour.
And just a follow up.
Nth of a kind, sorry. This is nth of a kind.
So first of a kind, what would be the estimate cost there?
It will be market competitive, so we're talking about $50 per megawatt hour.
Thank you.
Question about social acceptability for nuclear deployment. Where do we stand right now, and where do you see that headed, at least in the geographies you're targeting?
Yeah, so public acceptance has definitely been strongly on the rise now that nuclear has been recognized again as part of the solution for climate change. In the US especially, we now have strong bipartisan support. If you look at, I'm actually going to Congress soon, and I was looking up all the policies. It is truly amazing the amount of bills being passed and being suggested supporting nuclear, because we have the push of advanced manufacturing, we have energy security, we have job creation, and then more for, depending on what side you're on, environmentalism. So we see kind of from all across the spectrum support for nuclear. Something that additionally, I actually forgot to mention in the pitch is we also increase safety compared to current technology, because by integrating essentially steam generators into our vessel, we remove an entire class of accidents, which would be what happens if your pipe going from the reactor to that component breaks and you lose all your coolant. So we have increased safety. We see strong political support. So I would say acceptance, both from the public and government, is as high as we can hope for it to be.
And just to add to that, something that wasn't added, but that adds sort of potential acceptance for this design is that when you go from those big reactors to this smaller size, you can actually reduce what's called the emergency planning zone. For large reactors, you have this emergency planning zone, which is a 10-mile radius around your plant, where you have to basically be prepared in case some very unlikely, but potentially a severe accident happens. Whereas for these smaller reactors, with this increased safety, you actually reduce the emergency planning zone to the site boundary, which will increase sort of local acceptance and confidence in the plant.
Okay, maybe just rapid fire on the competitive landscape. As other SMR startups are starting to pop up, how do you sort of think of the top 1 to 3 things that you think really differentiates you in the landscape?
Let's put the slide on the competitive edge. So we like to think about the industry in these 2 main metrics. The first metric is maturity. So we talk about the regularity aspect, the fact that the regulator is already familiar with this technology. The second aspect is the operational aspect. So utilities or our customers need to know how to operate these. They don't have to train a whole new workforce. So in our case, they already know how to operate pressurized water reactors. The third aspect is supply chain. You need to have confidence in terms of getting your fuel, getting your components from the market. If not, you have to develop them yourself. And in that case as well, we have a competitive supply chain. The other metric is the system power density. And this is, we have many, many studies in the field that show that the higher system power density will allow you to reduce your cost of electricity. And so this is really where we shine, as you can see here. The fact that we have a compact high power density system will allow us to achieve that level of LCOE.
So green is this.
Mhm.
And this is the green.
All right, up next we have Upcycle X.
Good morning. I'm Ren, CEO of Upcycle X and a postdoc at MIT. Today, I'm thrilled to share with you the results of my decade of breakthrough journeys, including the core of my PhD thesis. Today, the world is now facing a global plastic crisis. Over 400 million tons of plastics are generated every year, accounting for 4.5% of global CO2 emissions. Do you know what this number means? Shockingly, this is the recycling rate of plastics. So over 90% of plastics are discarded, destined for landfills, incineration, or marine pollution. Why isn't current recycling system working? In theory, most plastics are recyclable, and this is what we expect from recycling, right? However, the reality is quite different. Instead of true recycling, what often happens is downcycling, where the quality of recycled plastics is lower than that of new or virgin plastics. Even worse, it is more expensive to produce recycled plastics than virgin plastics. So there's no reason for industries to use recycled plastics right now. The solution? Upcycling. Transforming waste plastics into higher value products is the only option to motivate whole industry to process waste plastics. With this, people will see plastic waste not as trash, but as valuable resources. Our solution is electrocatalytic upcycling, which uses electricity to convert plastic waste into higher value products. Our first reaction model focuses on PET waste, converting it into KDF, a premium animal feed additive, and TPA, a monomer essential for PET production. As shown by the market prices of our products, our methodology highly elevates the value of PET waste. And our process reduces plastic waste with zero CO2 emissions and no secondary waste generation. Additionally, we can offer KDF and TPA at lower prices than market average with sustainability badges attached. So for companies who care about their images, there's no reason not to choose our product, undoubtedly. So from 1 ton of PET waste, we produce 0.54 tons of KDF and 0.62 tons of TPA, generating about $2,000 in value while reducing a large amount of CO2 emissions. With the massive market sizes for both KDF and TPA, our TAM goes by $20 billion. This shows the immense economic potential of our solution while addressing global plastic crisis. Our key technologies include plastic waste pre-treatment methods and our cutting-edge nanomaterial catalyst, delivering exceptional energy efficiency of over 90%. And we have developed an efficient product separation technologies. So this whole cycle is detailed in my research article. And this innovative technology forms the core of Upcycle X, offering differentiated advantages. Let's take a look at our competitors' technologies. There are some companies like Brightmark and Plastic Energy that use thermal methods. Their process is energy intensive and they often accompany harsh CO2 emissions. And there are some other players that use chemical or enzymatic methods. They often face challenges like limited scalability and relatively higher production costs. Meanwhile, our technology, electrocatalytic upcycling, offers a game-changing alternative, which is cost-effective and sustainable simultaneously. So we can confidently say that Upcycle X will provide a realistic and economically viable plastic waste processing method.
And we're confident that we have the team to successfully commercialize this technology. So of course, Dr. Run brings years of experience in academia and a deep and rich understanding of electrocatalysis in this specific application. Then for myself, I bring years of experience in plastics manufacturing on both the projects and the operation side, as well as the business and strategic mindset from my education at Harvard Business School. So together with our complementary skill sets, experiences, and the resources that we have in both institutions, we know that we're going to be able to successfully build out this product and also make sure that we understand and serve our customers well. So now let's talk about who we're going to sell to and how are we going to sell it. So our first beachhead market is going to be focusing on the KDF revenue stream, and it's going to be focused on animal feed producers. All these targets are customers that are already purchasing these commodity products, and that's why we're strategically picking them. So our follow-up markets on the KDF side are going to be food preservative manufacturers, and on the TPA side, they're going to be PET plastics manufacturers. Now, in terms of how we're going to sell it, thankfully, we have a few options. So the first is the most straightforward one, and is that we build out the manufacturing process, become a manufacturing company, and sell these chemicals directly over to these customers. The next one is using this innovative technology and licensing it over to these big companies for them to integrate into their research and development departments. And finally, we can make modular systems or turnkey solutions where we basically put our manufacturing process into a black box and sell it to our customers for them to integrate and to operate into their facilities. Now, based on the insights that we've gotten from talking to customers and our insights on the industries, we know that the chemical sales route, selling chemicals directly to them, is going to be the thing that best serves their needs. But we're still going to maintain the leverage of these tools should we hear anything different or should there be any changes in the market. Now, this, with the chemical sales route, is the techno-economic analysis. I won't go into too much detail, but you could just see on the top right there is the unit economic breakdown on the costs. As well, on the bottom is just the comparison on the revenues split up by revenue stream. The biggest takeaway from here is that we're expecting about a 20% gross margin when we sell these chemicals directly to our customers. And then in terms of our timeline, in terms of what the next 5 years look like, there's just a high level view on the tech side and the biz dev side. But the main takeaways are that the next few years are going to be building out the technology and making sure that we can conduct trials and begin initial sales with our customers. And then the next couple of years is just going to be hammering down on manufacturing, making sure that we can make it lean, efficient, and also achieving further market penetration with our customers. So with that timeline, with that business model, with that technology, and more importantly, with this team, we know that we're going to be able to successfully fulfill our customers' pain points and clean up the plan in the process. So thank you so much for joining us on this journey, and we'll open up to any questions from you guys. Thank you.
No, I'm happy to go first. Thanks for the presentation. I guess, yeah, it's a really important topic, I guess, and you showed it nicely in your TA. So much of this is driven by the input, by the feedstock that's like driving all of this. I mean, that was the large gray bar there. So in terms of that from two sides, from both the technology side and the business side. From the technology side, what can you handle in terms of, I guess, impurities, mixed waste, dyes, everything associated with that? And then in terms of the business side, how do you intend to like secure that input, be it kind of post-consumer or pre-industrial or wherever else?
Yeah, I think that's a great question. So for the techno-economic analysis, we did many assumptions. So we assume 300 milliampere per square centimeter of current density and 1.7 voltage, and also 15% of impurity of PET waste. That is the assumption of the techno-economic analysis. So main cost driver is in the technology side, we should improve our ferritic efficiency, which is energy efficiency, and also we should make it larger for the current density because it directly affects the electrolyzer cost. So the two factors are really important for the technology side, and for business side, as you mentioned, the major part is input chemical cost. So getting some good contract with nice providers with a lower cost and high quality plastic waste, and also input chemicals like formic acid and KOH will be a great strategy to lower our input costs.
But I guess more specifically on that, you've said there's 15% kind of waste impurities. Tell me more about that. So, I mean, what would happen if it was mixed? What would happen if there are films? You know, would that break the electrolyzer, dyes, everything else? What have you demonstrated on that front that it can tolerate or can't tolerate?
Yeah, to compare with like thermal methods, which is really conventional in plastic recycling, the impurity like grease or caps or labels will highly affect the performance of the catalytic reactions. But we use the hydrolysis to dissolve for example, PET into ethylene glycol and terephthalic acid. So the impurity effect is a little bit lower than that of conventional methods. And also for feedstocks, the bale plastic PET waste and the flakes are existing, but the flakes one is more expensive. Like it is like $800 to $900 per ton. So we're not gonna use any flakes for the feedstock. We'll just use bale ones and dissolve it with hydrolyzer and use it as a feedstock for the electrocatalytic reactions.
Thank you. Can you please speak a little bit about the operation scaling and the cost curve of how you think about it, and especially the electrolysis part as well?
On the scaling part.
Yeah. So starting with the lab scale demonstration, I have already conducted research on the lab scale demonstration in South Korea. So we already did 25 to 100 square centimeter of scale. But if we conduct on 40 square meter of scale, then we can process 3 tons of PET. And our ultimate goal is to process 200 tons of PET per day. And it requires 2,500 square meter of electrolyzer. And for the cost revenue and positive revenue timeline, I think Jonathan can tackle that.
Yeah, I mean, in terms of revenues, so I mean, we have a good understanding of what our customer funnel is going to be and what it's going to look like. So, I mean, in the initial stages, it's going to be conducting trials to make sure that we get buy-on from these customers, of course, so that we can integrate it into their processes. And then from there, it's just going to start a short-term supplier agreements and then convert into longer-term supplier agreements. So I think if we go onto the timeline side, we might be able to see a little bit better on the biz dev side, sort of what that timeline looks like. And how it kind of compares to our scaling process when we go from that first stage that we had just seen in that first slide, and then going to that second stage at the higher production scale.
Yeah, just following up on that note, could you highlight the bigger expansion risk, especially on the electrolyzer side? Because it seems like right now it's mostly on the pilot demonstration. So what do you expect to witness as you kind of grow capacity?
Yeah, that's a great question. So the electrolyzer cells scaling up is really convenient and is already proven in green hydrogen industry. So we're expecting that processing 200 tons of PET using 2,500 square meter of electrolyzer will be is really possible to conduct. And the question is, how can we deliver the electrolyzer cost? Because typically the cost of electrolyzer is $10K per square meter. So it is reflected in the techno-economic analysis. So yeah, we are confident that given all the capital electricity operation costs, we can still generate 20% gross margin, and that means we can provide the products at lower prices than market average. So we're confident that we can make it happen in reality. So the main strategy will be delivering the finance for the achieving pilot scale.
Thank you.
You mentioned that on the business model side, you're leaning mostly towards actually doing chemical sales rather than the licensing or system strategy. Are there ways that you're sort of thinking about how to reduce cost for the first of a kind facility that you're building out in terms of co-location or other strategies like that?
Yeah, no, I mean, it's a good question. So, I mean, when it comes to the sort of chemical sales side, the sort of priority and kind of stemming a little bit from my experience back in projects and manufacturing is sort of making sure that we have a lean operation, right? That we don't have, I mean, obviously having enough reliability and making sure that we have safety when it comes to sort of safety measures in chemical tanks, but making sure that we don't have anything in excess, right? So that's definitely one of our main priorities when it comes to building out manufacturing process. I think minimizing the distance between us and our customers is potentially another avenue, as you kind of mentioned, right? We do expect transportation costs to be a decent chunk of what future costs could be on the OpEx side. So those are a few strategies I would say that we're kind of looking at on the manufacturing side. But I would say primarily it is just making sure that we maintain a lean operation and that we don't have any, or making sure that we streamline everything. Okay, thank you.
Thank you very much.
Great. Please help me welcome to stage Leighton.
Morning, everybody. Last one of the morning block. I'm Rourke. I'm a second year from across the river here at Harvard Business School, and I'm pleased to be able to share Leighton with you this morning. So today, consumers in the US drive on average about 35 miles per day, despite the fact that they're asking for a vehicle with 300 to 400 miles worth of range, meaning that on an average day, 85% of that capacity goes unused. In service to the energy grid, that capacity is worth over $6,000 a year. Why does that matter? Well, 28 million EVs on US roads by 2030, that unused capacity is the equivalent of 60 times the total volume of US connected grid storage. It's an astronomical amount of capacity. Simultaneously, our energy grid is changing. With the advent of solar and wind, energy is being generated, oftentimes at a huge mismatch with when consumers are looking to be able to use it. So when the sun shines or the wind blows, energy is being generated, however, not necessarily at the exact same time when peak demand occurs. This results in huge volumes of renewable electricity effectively being thrown away. Some forecasts put it north of 30% could be due to this mismatch. A massive underutilization of renewables coupled with a massive underutilization of storage are a natural pairing. And prior to school, I was at Ford working on this technology, but I saw that we weren't building an end-to-end solution. That's where Leighton comes in. Leighton provides the in-home hardware and software to connect you as an EV owner with 1,400 utilities across the country, enabling you to tap into this $6,000 worth of latent value in your vehicle, while also providing the inbuilt benefit of your vehicle being the equivalent of 4 days worth of home backup power. I can't get too much into our hardware right now, but the analogy I always like to use is a little bit like a Google Nest Smart Thermostat. It's a critical piece of hardware in the home, but the value proposition is really about the software and energy trading ecosystem built around it. So for instance, the critical piece of hardware is really two. One is the bidirectional EV charger, the thing that physically plugs into the vehicle that allows you to be able to charge and discharge energy off the vehicle. And the second is what we like to colloquially refer to as the grid gateway. The technical term for it is a hybrid disconnect switch, but Tesla calls it a gateway, so we've co-opted the term. The best operation you can kind of think of this is safe interfacing opposite of the utility and allows us to be able to physically disconnect in the event of a power outage, allowing you to be able to island. This combination of the gateway and the bidirectional EV charger, managed by and orchestrated by our home energy manager, allows us to be able to ensure that energy is flowing either into or out of the vehicle for safe use by the home or for export back to the grid. The big thing for us is that because we sit at the nexus of energy and automotive, there's a number of incumbents that are interested in our space. However, coming from an automotive background, we saw that folks were either focusing at it from a software lens, as well as there's some of these ancillary services around financing or some of the early energy aggregation tools. But knowing that it was going to ultimately take a full end-to-end solution, vertically integrated, to be able to actually unlock this market. And that's exactly what Leighton looks to be able to do. We offer this appropriate balance between hardware and software while also recognizing in order to achieve scale, we needed to be auto OEM and utility agnostic. So I had mentioned those 28 million EVs on US roads. That's the equivalent of $160 billion worth of storage capacity. And that's only with 10% of the US fleet moving over to electric vehicles. This is going to be an astronomical market, and it's an incredible opportunity for us. So where do we start? The big thing for us is in states like California that already are starting to suffer from this challenge of this balance between renewables, we're effectively starting to see this passive price signal consumers, effectively tiered electricity pricing at the residential level. So overnight, you might pay, let's say, 2 cents per kilowatt hour when demand is low. And at this 5 to 8 p.m. hour, when you have this perfect storm of solar's coming offline, energy demand is peaking as everybody starts coming home and starts making dinner, but also overnight wind hasn't picked up yet, you might pay, let's say, 36 cents per kilowatt hour. So the first stage of the business model for Latent is effectively to enable customers to pre-buy low-cost electricity in the off-peak, store it in their vehicle throughout the course of the day, and at this on-peak time, rather than run their appliances off of this high-cost electricity from the utility, effectively discharge it out of their vehicle, enabling them to take advantage of this about 25 cents on average arbitrage value, equivocating to about $1,400 a year versus customer cost savings. A portion of that is shared back with Latent. The reason why this matters for us is a little bit like the stock market. The energy wholesale markets have this real-time price volatility. And so what's interesting is the rules used to be, in order to trade in the energy wholesale markets, you used to need to actually be a grid scale power plant. However, now, as long as you're an aggregated pool of assets of at least 100 kilowatts in size, ergo 10 vehicles in a neighborhood, you can now trade in the energy wholesale markets on behalf of those assets. That's exactly where Latent looks to be able to be in the long term. Effectively, first rights to be able to aggregate this group of you and 9 of your neighbors to be able to trade power on the energy wholesale markets, transitioning from this $1,400 cost savings model to realize this full $6,000 worth of value by offering that capacity to the energy wholesale markets. So as it gets into our business model, the big thing for us is how do we align the stakeholder incentives? So the lesson for us really came from the first generation of home solar. It wasn't those with the best technology that were the vendors that won in the end. It were the ones who made it as easy as possible for a customer to say yes, ergo, no upfront cost. Simultaneously, utilities are giant regulated monopolies that are not necessarily incentivized to be efficient with their capital. They're actually, in the best way that the states have found to put the pressures of the private market onto the public sector is effectively regulated return on capital. Utilities are effectively incentivized to have as large a balance sheet as possible. Ergo, they're actually the ones who are incentivized to be able to buy our hardware and to pay for the cost of install. This creates a win-win-win for the ecosystem. The EV owner has no upfront costs and can take an arbitrage savings out of their vehicle. Latent doesn't have a recurring cash flow model and takes a portion of those savings, allowing for the aggregation. And the utility is able to contribute directly to their bottom line. This creates a really stable flywheel that offers us to be able to create a giant business here in the US. And even with a reasonably small market share, it offers significant opportunity for growth. The big thing for us is our team. For me, I came from an electrical engineering background, started out my career in self-driving at Waymo and ultimately at Ford before transitioning to electric vehicles. And then most recently in my time at Harvard Business School, spending my night job on the startup and day job working in grid scale batteries and wholesale power trading down in Texas. My co-founder Baha is a PhD in electrical engineering who started out his career at Mercedes as a part of their electrification team. We worked together at Ford in self-driving and electric vehicles. And now he's at Renesas, which is the leading provider of silicon for automotive applications. We're supported by a world-class set of advisors that have been at the cutting edge of energy, automotive, and technology. And we'd love to bring some of the folks in this room on board. But this wouldn't be the climate and energy competition if we didn't talk about carbon impacts. The only resources on the grid right now that can potentially solve for that issue of when solar is coming offline and energy demand is peaking are effectively open cycle natural gas turbines. They're horrible polluters, and batteries offer an alternative. So for us, that effectively enables us to be able to offer this abatement of 99 million metric tons of CO2 directly that would be emitted by these open cycle turbines, or alternatively, the bigger emitter, these NOx emissions that come from these same turbines, which comes out to about 566 million of CO2 equivalents. Simultaneously, this alternative building redundant batteries in the ecosystem, as opposed to tapping into the batteries that are already used, offers us a savings of 85,000 metric tons of potential lithium. We're in the middle of raising our seed round right now. We actually just had a big win this week in terms of bringing on an additional investor, and we'd love to be able to bring a couple of the additional folks in as we close out our round in the following weeks. At this point, I'll turn it over to questions, and thanks so much for your time.
Thanks so much for the great presentation. Curious too, I know that you didn't focus on sort of the hardware or the technical side in the presentation, but would love to hear a little bit more about what you're thinking about for sort of the technical roadmap ahead and what you need to prove out within the seed framework.
Yeah, so a couple different lenses that we could potentially go at that about when we talk about the actual dynamics for the seed round. So part of this is this transition from single directional EV charging today to more of this bi-directional EV charging. So for those who aren't familiar, a single directional EV charger kind of more or less looks like a smart switch. When you transition to bi-directional EV charging, you look more like a backup generator. And so for us, it's not only these technical interfaces to the vehicle itself. So for us, transitioning into this actually enabling this communication protocol directly between the bi-directional EV charger and the vehicle itself, and then subsequently building in that communication with the grid to be able to operate safely. What I didn't talk about necessarily when I was referring to the grid gateway, one of the classic examples that's always used for this to talk about the safety critical nature of this function is, let's say you've got a power outage. Your utility, let's say your power line goes down, the utility will send out a utility line worker to go out and service your area of line. But if you're a backup generator, your home solar, or in this case, your EV is leaking power back to the grid, that line risks being electrified and you can kill the utility line worker. And so naturally for us, there's actually a critical component to this is making sure that we actually have the appropriate certifications in the market and then actually to be able to be actually approved on these lists in the state of California to be deployed. So that's really what we're focused on, is building this critical piece of hardware and then more about the certification process.
Question about the contractual aspect of your model. So is there like a standard contract embedded in your solution that basically manages end-to-end the transaction, the selling and purchase of electricity? And how do you handle the variability in terms of regulation from one region to another? If so?
Yeah, so maybe two separate questions. One is maybe tied to financing and kind of business model structure, and then maybe one is kind of tied to grid dynamics and energy regulation. Happy to be able to touch both. So the big thing for us in our go-to-market when we actually talk about those regulations from a technical standpoint. So one is key is that I don't know how many of you in the room have had a chance to be able to drive an EV recently, but there's effectively this transition when you actually look to be able to, there's three ways that you can manage a transaction at a high-speed charging station. A little bit too into the weeds, but we'll do it just for the sake of it. It's basically this communication protocol. You can either pay with your phone, you can pay with a credit card, or the transaction is actually managed over the cable. The technical communication protocol that allows for that transaction is called ISO 15118-2. The reason why that matters is the evolution of that protocol that goes from -2 to -20 builds in the incremental handshake that actually allows for the net discharge of electricity off of the vehicle. So the big thing for us right now is we're actually launching, primarily we're not science risk necessarily, we're more stakeholder risk. And so how do we abstract away that need to be able to interface actually with the OEM? It's part complying to this -20 standard. And so for us, being able to build this charger that communicates with it, that helps to abate that potential need. I'm assuming part of your question was also talking about the contract from actually a utility standpoint as well. So there's multiple different ways that this can potentially be configured, and this kind of depends on the energy market that you're operating in. So for us, depending on if the financing structure looks more like a tolling agreement, it's more about being able to build in those financial services. So for those who aren't familiar, if you build a solar power plant, let's say you get a 30-year power purchase agreement, a tolling agreement is effectively a similar structure where it says, I offer you this amount of capacity 10 years from now for this intraday arbitrage. There's a way that we can effectively package up these EVs together and offer them to be able to get project financing that looks like almost like a distributed tolling agreement. And so that's part of exactly what I'm thinking your question was digging at.
That's great. Thanks.
I had a question more on the jurisdictions that you're targeting. It sounds like you want the pilot deployment to be with like a California utility, but would love to better understand the expansion and like what are the key markets that you're looking at targeting?
Yeah. So the big thing for us when we think about the rollout of the business model, kind of to that point of we're stakeholder risk, we're not necessarily science risk. It's how do you abstract away aspects of this problem of you got a 1,000-pound gorilla of a utility, a 1,000-pound gorilla of an OEM, and then you also have a naturally fickle customer. And so for us, the early stages of the walk of the business model are kind of first and foremost to be able to actually abstract away the utility and abstract away the OEM. To the answer about using vehicles that comply to this -20 standard, that abstracts away the OEM. The big piece for us why we're launching California are these time of use rates. This idea of actually a retail customer doesn't actually need to engage with the utility. They're already being charged on this tiered-based pricing model. So as long as we're a certified device that can be deployed in the home, we can actually enable you as a customer to be able to take naturally advantage of this cost savings that would otherwise be as a part of your utility. The big thing for us is as we transition, We actually then flip into this second stage of the business model where we're doing this energy aggregation, and it's going from your customer cost savings to this actually getting paid a check by the energy wholesale markets. So in terms of market expansion, California is great for us because they have these built-in time of use rates that have this greater than 25 cents arbitrage. They also have this regulatory implemented that allows us to trade in the energy wholesale market. But the big thing as we look about expansion across the country, it's kind of this Venn diagram of you can think of renewables increase price volatility, and then storage helps to suppress that volatility. So it's basically where is that Venn diagram of where is renewables outpacing storage, and also where is their EV adoption. So for us, that starts out with, for instance, California and the CAISO market being over across in New York and NYISO, and we've talked to a couple of utilities in the space, but we're also starting to see some rapid growth in the center of the country in like SPP and ERCOT. And so it really is about kind of tracking that over time and building this flywheel.
Thank you.
Can you speak a little bit about the competitive landscape? Like I'm more familiar with WeaveGrid, but if you could just kind of tell me how you differentiate yourself and how you think about yourself versus who's out there currently.
Yep, it's a great question. And I think there's part of this, we could spend potentially an hour on the competitive landscape, but WeaveGrid, EV Energy, and Fermata are always ones that we get frequently referred to in the vehicle to grid space. So WeaveGrid specifically, it's interesting, this smart switch construct that I talked about previously with single directional EV charging. Because these single directional EV chargers are effectively a smart switch, it's relatively easy to wrap an API layer around it. And so a WeaveGrid or an EV Energy, they're effectively selling the service to a utility. So they're saying rather than at this 8 p.m. hour when you flipped from the time of use rates and you would otherwise have this secondary demand spike, they're allowing kind of this more smooth curve, incremental aspects of the fleet start charging over time. The difference is once you transition from that smart switch construct to the actual bidirectional and you go into this more generator, there's actually there's a tighter coupling between that hardware and software. So for instance, the closest to a WeaveGrid that we've seen is like, for instance, a Fermata that has been closest to hardware in that hardware to software spectrum. And we've actually seen them continue to actually go out and contract with external manufacturers. And they've run into issues where they couldn't tell if it was the contract manufacturer's hardware, their firmware, or Fermata's software. And so that told us we ultimately can't avoid the hardware problem.
Thank you to all the semifinalists who just pitched. This gets us through our first block. We'll take a short coffee break, stretch your legs, go to the bathroom. Bathroom is right through those doors. And we'll just start shuffling back in right before 10:40. Thank you. Hey everyone, please start finding your seat. Great. Thank you. And well, let's please help me welcome to stage EC Cubed.
Hello, everyone. We're EC Cubed, and we're going to be telling you about our concrete energy storage solution. So if you look over the last 30 years, the energy demand in the United States has been surprisingly stable, despite various shocks and economic crises. But that's now exploding and exploding very rapidly. It's projected to rise almost 20% in the next decades, and 2/3 of that is due to AI and data centers alone. And that is putting an incredible strain on our grid, a grid that's already near capacity. It's not optimized for renewables, and frankly, it's not meant for the high power demand of data centers. So if we take a look at this problem a little more in depth, it's complex, but let's look at a simplification. A typical hyperscale data center of the kind used by Microsoft or Google might have an average demand of around 70 megawatts. But they have fluctuations that go above this demand, and so they need to account for more and overcommit to a very high amount from a single supplier, say 100 megawatts. And if that supplier goes offline, they want to have a backup. So therefore, they go to a different supplier with another energy contract. All in all, that results in overcommitments to energy contracts in up to $100 million annually, much of which could be avoided with proper grid-level energy storage. If we take a look at the current energy storage landscape, shorter duration storage is dominated by lithium-ion batteries, and there's many solutions for longer-term storage, such as PSH, with a myriad of other technologies in between. But they all have pros and cons, and frankly, even the DOE admits that none of these alone can tackle the future storage demand, and instead we need to invest in diverse, cost-effective, and sustainable storage solutions. But what if the entire data center, its floors, its walls, its foundation, could function as one massive battery? We're here to tell you that now it can. At MIT, we've developed and patented EC Cubed, a concrete energy storage solution. By embedding nanocarbons directly into ordinary concrete, we've created our EC Cubed electrodes, which can then be assembled into a patented EC Cubed supercapacitor and then stacked to form structural and energy storing EC Cubed concrete elements, such as columns, beams, or foundations. Importantly, EC Cubed tackles many of the issues faced by existing solutions. First of all, we leverage this architecture of a supercapacitor, meaning that we're able to achieve 95% efficiency, even after 100,000 cycles. This means that we can build and power long-lasting structures without the degradation issues faced by batteries. And while supercapacitors typically suffer from more rapid self-discharge, the beauty of a concrete solution is we can simply increase the thickness of our electrodes in order to increase the discharge time and fine-tune the properties for specific applications. Moreover, the materials we're using, unlike lithium or cobalt, are globally abundant. Nanocarbons are found all over the world, and cement and concrete is actually the second most used material on the planet after water. What this means is that even though supercapacitors typically have a lower energy density than batteries, we can play on this vast amount of concrete used to produce a solution that can actually deliver a massive amount of energy, upwards of 20 to 30 megawatt hours for a typical data center. Moreover, the materials we're using can be compliant with sustainability goals and be produced from sustainable sources, and they don't pose a flammable risk or fire hazard the way batteries might. It's also deployable. So if we think about how this EC Cube would be made, it all starts with our company, which brings together structural engineers and electrical engineers to continue R&D on this technology, produce IP, and deliver tailor-made designs for clients. We then partner with precast concrete plants and make just minor adjustments to their ongoing operations, namely installing silos to store carbon black and renting some of their concrete beds to produce our EC Cubed elements with just minor modifications. We then deliver it on-site using existing supply chains and infrastructure. It's also cost-effective. So if we take a look at that same example earlier of the hyperscale data center, and we build that same data center now instead with EC cubed concrete, we're able to save significantly on the overcommitments that these companies typically make to the grid, therefore saving them around $30 million annually or $300 million over the lifetime of the facility. All in all, that means that after an initial investment, EC cubed pays for itself in just under 4 years. And if we take a look back at that energy landscape, EC cubed is actually more scalable and deployable because of the materials that we're using than most technologies. So much so that even ARPA-I has called energy storing concrete an opportunity to solve US infrastructure challenges. In terms of our TAM, we have a $7 billion market right now, and we're initially targeting a much smaller SOM in just the US of newly built data centers. In terms of our capital plan, we're looking to raise about 100,000 this year in order to prove scalability with a pilot. What that means in practical terms is that we're already in talks with both a data center and a precast concrete plant in order to develop a 1 meter cubed concrete slab that can power a one-use server rack that's automatically ensures compatibility with the existing operations of those partners. Next year, we'll be looking to increase our financing through pre-seed and seed funding in order to sell our first units, starting with non-structural elements such as pavements, and then moving on to Series A funding in the future in order to actually support structural applications and then scaling up operations further down the road. We have a robust team that spans technical, entrepreneurial, and business backgrounds. And we've actually have a good track record of working together both on this project and on others at MIT under the tutelage of 2 esteemed concrete expert professors. And together we've taken this technology to new heights. So it all started back in 2018 when we actually, the first invention disclosure was filed for this technology. And the project really kicked off a few years later when one of my co-founders, Damien, joined the project and developed the first working prototypes that could first power an LED, then power some small handheld electronics, and now more. The project escalated a little bit more when myself and my other co-founder Ariel joined, bringing our physics and business backgrounds that have allowed us to increase the scale of the technology, develop larger, more structural prototypes, and we're now filing our 3rd patent and looking forward to developing that pilot project that I mentioned a little bit earlier. But data centers are just the beginning. This $7 billion market is pretty small when we think about how much concrete is actually used around us in the world, 12 billion metric tons every year. So let's think further. What about other critical infrastructure? Medical centers, military bases, airports, other energy infrastructure, or even further than that, concrete applications in the commercial and residential spaces, entertainment venues. All this opens a market opportunity of almost $500 billion. So we hope that you'll join us in a world where our infrastructure doesn't just consume energy, it stores it. Thank you.
Really great concept, guys. Interested to hear more about how you're thinking of integrating this technology into the typical construction process. I know you talked a little bit about precast concrete, pavers, that strategy, but how is it sort of going to look as you increasingly deploy it onto sites?
That's a great question. And here we have to imagine that concrete is a world where all technologies implementation is very slow. That's why we will start with non-structural components like pavements, then components which require lower strength like foundation and so on. How it will look in real life. Basically, with partnership with precast plants, that's where the whole adventure begins, where basically we're going to have to tweak the current or existing operation, which will include installing silos, mixing procedures, and then slightly changing the operation. But the most important part that we are using existing and leveraging existing supply chain and existing precast plants, which are built all over the world, and that existing supply chain exists. So our solution is just slightly modifying existing operation. Simple example is another startups like Carbon Cure, which have completely different approach to reduce CO2 impact of plant operation, but they also use existing infrastructure to just tweak some properties.
And just sort of adding on to that a little bit, I think that's very important because the construction industry is very averse to change usually. And so doing something that's as easy to adopt for them is perfect. And at the same time, it means that we can actually save our costs. If we don't have to open up our own plants, for example, that's really saves on the CapEx and allows us to leverage the existing infrastructure to deliver solutions as quickly as possible.
Can you elaborate on how you measure and assess your environmental impact, especially in light with the fact that you're tied to data center operations by drawing from different types of utility grids? Thanks.
Maybe I can take this one. So first of all, concrete is already there in data centers, right? So we're not going to add into the environmental impact of the data centers, but we're already thinking into using low cement, sustainable cements to lower our environmental impact of concrete. Now about like the tweaking that we're doing to make it conductive and energy storing. We're using nanocarbons that can be produced through sustainable process. So very low environmental impact, or even neutral environmental impact. And beyond that, if we compare our system to the coupled system of the data center concrete and the battery, we don't have either hazardous waste nor recycling problems, because even after our concrete stops storing energy, after let's say 50 or more years, we can still be used as a structure. So we're still functional.
Yeah, I was curious about how you think about talking to data centers and kind of beyond that, like maintenance component, the regulation component associated with all of that. I mean, these are exceptionally expensive servers, and you're going to put an energy storage unit underneath them, which may fail, hopefully won't, but there's just an extra consideration there on their own reliability and everything else. And I'm wondering how you think about that from a business point of view.
Yeah, so I think what you're bringing up, the policies perspective is very important to us. So given the fact that we're creating a multifunctional material that sort of focuses both on the built environment and on energy, these are two different sectors that actually both face quite a lot of codes, regulations, standards that we need to adhere to. Admittedly, on the energy side, our backgrounds don't necessitate that, or don't give us the end all be all to that, and we'll definitely be looking to hire actually probably later this year to find some help on the policy side, and then look to bring on a full-time policy consultant as quickly as possible. But at least on the infrastructure side, we have some good experience with Damon actually being involved in creating some codes for highway standards, and so sort of navigating both of those is definitely very important as we look forward to the future.
And maybe to elaborate on that, just to specify, because we have the architecture of a supercapacitor, we have the regulation of a supercapacitor compared to a battery. So we have advantages to that type of energy storage. For example, let's say in an urban environment where they're subjected to flammability, and so people are very risk averse to that. Let's say, for example, New York Metro Station. Well, because we're made as a supercapacitor, we don't have these problems. We could be also deployed in that type of markets.
I have a question on the market opportunity because it is massive, and I'm curious as to why like data centers were picked as the initial opportunity versus some of the others. Is it mostly because of like the high build expected over the next few years, or any other factors? Because
Yeah, great question. It's easy, I guess, to get sucked into the fact that data centers are in the news cycle all the time. We tried not to do that as much as we could, but the truth is also that we were looking for an application where there's a high demand for energy, and that there's a lot of concrete used, and data centers sort of fit that bill really well. We've done quite a bit of market research through various programs like the NSFI course to sort of validate these assumptions, and we've also been encouraged by the fact that just in our own sort of discussions or our work that we've done on this at MIT over the last 7 years, people from data centers have come to our labs and said that we're looking for green technologies that we can add to our infrastructure before they even knew about our technology. And then when our technology became a little bit more publicized in MIT News and various media outlets, actually more and more of these data centers started reaching out and saying, this is interesting. We're looking to learn more before we were ever thinking of applying this in data centers. So that was sort of a good point for us to see that there is market traction before we moved forward.
And why data center? Also, because energy consumption and stabilization is also important. So our material not only can store energy, but stabilize due to natural function of supercapacitor, peak shaving and so on. So that's kind of natural. Second, to build upon, real estates in Brazil are very interested in that kind of management on in integrated grid in South America. And lastly, we thought, of course, and we are considering other applications. We can imagine foundations of a wind turbine, where currently we cannot take all the big energy spikes that are created by regular batteries because of that high rate capacity. So we could grasp that part. We can also imagine that all barriers, coastal concrete structures could help with energy big shaving and help current energy storage systems, because currently if you would take, let's say, batteries, these systems can complement them beautifully by those functionality of kind of supercapacitor leaning towards battery. Thank you so much.
Thank you.
Thank you, everyone.
Thank you.
Sorry. Hello, please help me welcome to stage CEP.
Good morning, everyone. Good morning, everyone. My name's Tianshu.
My name is Chen Yang.
Today, we're launching Hexaspec to revolutionize cooling technology for future GPU manufacture. GPUs are generating so much heat that you can practically bake a crunchy pizza on it within a game or two. And some of the high-performance ones might even double as a barbecue grill. And the main problem lies in the heat generated by the chips. On each B200 GPU, 208 billion transistors generates over 1,000 watts of heat. Now multiply that by 72 GPU plus 36 CPU on each of this latest AI server. It generates a staggering 132 kilowatts of heat to be dissipated. Each data center might house over 1,000 of such racks. Well, Jensen, you may not need your hammer now, but you sure need a better thermal management. And such heat is raising real concern for our residential supply. Data center energy consumption will reach 8% of global greenhouse gas emissions by 2030. And cooling nowadays accounts for up to 40% of total energy consumption. For every conversation you have with ChatGPT, it can take a full bottle of drinkable water just to cool it down. And this is getting worse. Latest GPU design doubled the generation heat within only 1 year. With the rise of AI, the heat management problem of chips is becoming bigger, hotter, and more energy intensive. That's exactly what our customer cares. Data center demands higher computing power with less resource intensity. Design house set thermal specs to achieve those demands, and then chip manufacturer fabricate the chips accordingly. Hexaspec directly provide advanced packaging materials to the chip manufacturer to help them address all the key values during this chain. It's a complex chain, but with a simple solution. And for chips, performance equal profit. TSMC and Samsung were the dominant manufacturer for all the iPhone chips until TSMC achieved a 4 degrees Celsius lower surface temperature, which further boosts their battery time. As a result, Samsung lost all of their remaining orders, and this 4-degree heat management secured a $4 billion profit every year. As the gains from transistor scaling becomes marginal, advanced packaging serves as the method to improve the computing performance beyond Moore's law. Through this layer-by-layer stacking of transistor, it not only protects the inner ICs, but also it speeds up the devices without making the transistor smaller. And the latest investment from TSMC this week are mainly focused to build up the very first 2 advanced packaging foundries within the United States. It's not only continuum of more, it's more than more.
In this AI booming age, when other ventures focus on passive cooling outside the chip, like heatsink and TIM2, Hexaspec mainly focus on chip itself for better thermal management. However, the traditional packaging materials have not changed over 60 years. Those that present low thermal conductivity and poor protection. Hexaspec, making chips more thermally conductive, enabling faster and efficient extraction. Our technology can improve thermal flexibility for chip design, and our better protection can facilitate for compatibility with future immersion cooling. More specifically, our sustainable novel inorganic feeders offers ultra-high thermal conductivity, improved protection. They can cool chips faster reduce surface temperature, and further save tons of cooling water. Lower surface temperature can enable GPU works on high efficiency mode, increasing its performance by up to 40%. Moreover, better thermal management can potentially offer 10% more transistor in chip design. Hexaspec also promote sustainable practices. We can help to save 200K per year and reduce 16 million gallons of cooling water per year per data center. With 900 more super data center around the world, we are offering millions of dollars in savings along with energy conservation. Compared to other existing and new materials, Hexaspec offer higher thermal conductivity, low cost, better quality control, and compatible with current production line.
We have conducted over 200 customer interviews across the entire chip community, not only to validate our market, but also to attract industry clients to work with us. Our beachhead market will be the data center GPU chips advanced packaging, which faces the most significant heat dissipation challenge. Afterwards, we're going to leverage Hexaspec as a thermal management solution to other market, including battery cooling and wearable technology. For the past decade, we've been working on refining our material studies. We've filed 2 patents, published in high-impact journals, and refined our business plan through customer interviews and pitch competitions. Now, we're advancing to product development with our industry mentors using real industrial standard. We're also part of Center of Chimes, which bring up key universities and industry clients within the United States to develop next-generation chip devices. This also provides us with a channel to work with our future customer. And for the upcoming new product design, we're going to design a real chip with the manufacturer and design house. After the rigorous test and the compatibility test with current production lines, we are ready to launch a full paid pilot testing to develop a new, more powerful and sustainable chip with Hexaspec on it. From the Stone Age to the Silicon Age, materials innovations have always driven technology progress. We are a team of passionate PhDs and material scientists with working experience in semiconductor manufacture before. Please join us in our journey to disrupt this cooling market and unlock computing power for the future of AI. We are Hexaspec. We help chips beat the heat. Thanks.
Thank you.
And now we're ready for questions here.
Oh, I'll go first. It went through quite quickly the moment where you talked about actually the material innovation.
Mhm.
It looks like it's a boron nitride innovation. Can you tell
Yes.
us a little bit more about that material, what it's kind of embodied in, I guess, the properties, the
Yes.
anisotropy, or whatever else is relevant here?
Yeah, so we focus on low-hanging fruit. Boron nitride is a ceramic material. The key thing is it's one of the only few material that can be both electrically insulating and thermally conductive. And this is perfect candidates for chips packaging, avoid leakage here. And this material is not something rare, it's everywhere, even in your cosmetic, but people use it as a lubricant. So make them qualified to be used in chips manufacture. The morphology is a key thing. In general, the thinner the nanosheets, the better the performance. So that comes our other innovations here. We leverage the industrial bomb technology, and each bead collision will exfoliate the materials thousand times, increasing the efficient. We also have some data-driven process like the secret sauce here to increase the size distribution and engineer each material surface to avoid aggregation and dispersion. Yeah, improve dispersion. Sorry.
And then on the embedded piece, how are you actually including this into a chip?
Yes. So this is a very early prototype here. Looks like the chip thing, and the final product will be a composite here. We're not going to only have the feeder, we have the binder here developed too, and that's under patenting. And this one will be directly, the material will be sent to the packaging company, and it can directly fit it into the current production line. And this is the machine they're used here. We're focusing on the molding part, and that's the current molding machine used in the TSMC manufacturer, and just directly fitting here. And my co-founder actually played with this one before, so we're confident to ensure the compatibility and engineer our materials.
More of a general question or something to consider going forward. What's your take on the geopolitical tensions that are going on and how it could impact your market and your expansion?
That's a wonderful question. So right now, US want to bring advanced packaging to the United States. That's why they push TSMC to move their foundries here. And by the end of this decade, they try to achieve 20% of the domestic production of the new AI GPU. Now it's like 0. And this is a good tailwind for us to benefit. We can be the domestic supplier for next generation packaging and to avoid all the tariffs. And it's helping with our customer like TSMC and also with the domestic like US semiconductor development here.
Just a question on the pilot expansion. So what are the key technical risks you're expecting from like the performance side of things?
That's a very great question. So the original material hasn't really changed for 60 years because current production tools and parameters are designed for this old materials here. And during our customer interview, we know they don't want to change the production line. That's a key thing. So make sure like it's compatible with it is a key thing. Our material can be directly used in the current tool is the technical milestone we need to get over here. And it will be demonstrated in our future pilot testing and NPI here.
Can you elaborate a little bit more on how you're sort of envisioning fitting into the value chain and who you sort of have to disrupt in order to access the right point in the value chain?
Yes. So semiconductor has AI GPU has a huge, very complex AI chain, and our customer will be directly the chip manufacturer here. So like TSMC and maybe some material supplier from Japan. They're the big players here, But to push this forward, like Design House has huge decision-making power. They're the one who designed the chips here, and they're specifically like thermal design manager. They care about the thermal here. So for the coming discussion for the pilot testing, Design House, Hexaspec, and chip manufacturer will be host a meeting together to push this forward.
One more question. So how much do you have to tailor each design for the specific chips, like from a percentage standpoint? Yeah.
Yes. So that goes to the pricing and the financial a little bit. And the current epoxy molding compound, it takes around like the price ranges to $13 per kilograms to $40 per kilograms. And our material, the cost is around like 40, and the price will be set at 70, and to reach a steady growth rate in the future. And this packaging material currently take like 20% of the total packaging here. But in the future, as I mentioned, advanced packaging not only serve as a protection now, it serve as a way to make the computing more powerful. So the value actually change in the future. And we have, during the customer interview with the packaging manager, we told them like, what we feel with the price here increase. And they mentioned if the performance good, the price is not something they really like concern here. And we also add values. For example, current GPU, when they're put into the immersion cooling, and they found some liability degradation because this material was never designed to sustainable cooling liquid here to immerse there 24 hours. And we can also add value to the protection part. So a lot of the values can be translated to increase our gross margin in the future.
I think so. Given that, and absolutely, and you're saying you want to be a kind of material provider and work with these. How big do you see this company could be then in the kind of 5, 10, 15-year horizon?
Yes. So
capturing on that value that you talked about, that actually you're delivering all this value, but as a material provider.
Yes. So we're going to start, that's like the production capacity. So the early part, we can start to feed around 21K chip packaging per week. And right now, the TSMC in US, they can provide around 500K per week, and this will be increased dramatically because now it's like testing part. And if the performance is good, as we mentioned, chip marketing is like performance equal to feed. If it's good, then all the chip market can be all the future chips can be made from Hexaspec here.
And like beside of the like a typically GPU and logic chip, we can also apply our material in like the future memory. Like we believe Micron, they produce a lot of great HBM and high bandwidth memory. Can also apply our material and to do the heat dissipation.
Yeah, packaging is everywhere, not only logic memory, logic chips here, and also memory chips. So it's like computing and storage here. And for the storage, the heat dissipation is the key barrier for them to make it more powerful. That could be a thing, a market for us. And we think further ahead, AI chips can be everywhere in the future, not only in data center, maybe our wearable technology like VR, AR, or even bring computer interface in the future. And for this case, it will be hard to use active cooling, like the liquid cooling or like water cooling to cool it down. It makes no sense for us to immerse in the cooling liquid every day. So making the chips more thermally conductive, it's a must-to-go barrier for the industry here. Thank you.
Awesome. Just there's a couple minutes here to put up some chairs for this very exciting panel that we have coming up. And yes, great. Great. Please help me welcome to stage our panel, who is going to be moderated by Limor Spector, who is the president of Ventures, and she helps scale startups so that help them reach the next level. And she'll introduce the rest of our panelists. Thank you so much for doing this.
All right. Maybe switch to that one. Okay, excellent. Thank you, Alejandro. Pleasure to be here. And thanks also CETA and the rest of the organizing committee. Very excited to be here and to talk to you guys a little bit about investor startup relations. We've got an amazing group of panelists here who may decide what order to sit in. And so we've got a good half hour now just to talk a little bit about the different interactions that we have. Before we get started, let me butcher some introductions here from each of you. And I'm not going to go in any particular order here. But first of all, we've got Michael Alexander, co-founder and CEO of Addis Energy, which is a startup really pioneering a net energy positive zero emission pathway for ammonia production. And Michael has had a ton of experience in the energy sector, roles at Marathon Petroleum and at Shell, and a pretty impressive academic background, as with I'm sure many of you here, with an MBA from HBS and also a degree in chemical engineering from Cornell. Next, we've got Michael Kearney. So, you know, we try to keep the Michael names the same so you guys can remember, who's a general partner at the Engine Ventures, really focusing on climate change mitigation, which is near and dear to many of our hearts. He is on the board of a lot of different companies, including Addis Energy. So this should be interesting for us. At Macero and Veer, he also helped launch Ambry, and he has an MS and PhD from MIT and a BA from Williams. All right, then next we've got David Miller, who has been spending over 25 years in startup management and seed stage investing. He's the executive managing director of the Clean Energy Venture Group. Sorry, thank you, appreciate that. And has served on the boards of a lot of different companies, including Boston Materials, Valexion, Noon Energy. And he's also a research affiliate at Sloan. And he has a lot of degrees from MIT as well, including PhD and bachelor's and master's. And then yes, a lot of MIT connections here. So on the end, we've got Sareen Grama, who's the co-founder and CEO of Transera, which is a startup developing high-efficiency air conditioning technologies. And prior to that, he actually founded Promethean Power Systems, which was a thermal battery for cold storage. And he's also a founding member of Greentown Labs and is an MIT D-Lab instructor and entrepreneur in residence. He's also a trained electrical engineer and has a master's in engineering management from MIT. So welcome to all of you panelists. Maybe just to say a couple words about myself. My name is Lee Morris-Spector, as Alejandro mentioned. I lead ventures for GE Vernova, which is a 130-year-old startup, which was founded this year, but also has the heritage of General Electric. We have about machines that generate about 25% of the world's electricity. And we have a focus on generation, electrification, and wind. I myself have spent the last decade or so in incubation venturing at General Electric and other Fortune 50 companies, on the board of Think Labs, board of AirJoule, and certainly advising other startups as well. My degrees are from Harvard and from Stanford in physics, so unfortunately I am not really into all this MIT stuff going on here, but I will try to make sense of it for the next 30 minutes or so. So welcome, everyone. I think maybe we'll start off, since we've done some intros, with a little bit of an introduction to how to get to know one another. And maybe I'll start with you guys over here. Talking a little bit about kind of the first meetings, right? And so maybe starting with you, Michael, how did you prepare for that very first meeting with investors? How did that meeting hold up, and did your strategy work out perfectly?
So we met Mike, Charlie, my co-founder, and I actually like 30 feet away from here at an engine event. It was like a pizza hour where Charlie and I were the only two people with jackets on. We came dressed up to impress. And when we started talking to Mike, we cornered him while he was eating pizza. And he quickly told us that our venture that we were working on was good, exciting, but absolutely nothing he would invest in. He was more supportive than that, but it was also pretty clear, like, this is not in the engine's purview. So that was, I guess, not exactly how we thought that would go. At the same time, though, I think it did help Charlie and I drop our guard, be more authentic, ask all the crazy, silly questions that actually showed how much we'd been thinking about things, at least I hope. And then later down the line, we got connected with our academic co-founders. Actually, Mike helped make that connection. And then all of a sudden now we have this differentiated IP coming from MIT. And so that is really what we're building and scaling to commercialize now. So I guess that's the short version. Yeah, maybe a little less typical than the usual.
So I think the color from my side, we hosted this event here on with the goal of getting to know folks like yourselves and understanding kind of what people are interested in. And Michael's right. He and Charlie were the only ones wearing blazers at this event. And they came up to me and they're like, and Charlie, Michael's business partner, is from Texas, and speaks with a Southern accent. And he was like, we're going after geologic hydrogen. And this was almost 18 months ago. Yeah. And they were telling me about, the building an exploration company for geologic hydrogen resources. And I was like, that's cool. Like, definitely a hot area. And in my mind, I was like, that's not for us. Not because the idea was bad. It was because we don't invest in development companies. But I had earlier that week met with Tim Abate and Yetmin Cheng at MIT, who were telling me about their technology to actually do geologic extraction of ammonia. But there was nobody working on that from the like as a potential founders of the company. And so in that moment, when I'm talking to Charlie and Michael, and the only thing that mattered to me was like, I just have to tell them they need to go talk to Yet and Tim and then just see what happens. So that's what I did. And it was like December, maybe November. Yeah. And I thought nothing of it other than some folks working on geologic hydrogen that I put in touch, and maybe they'll, like each other and connect and work together at some point. 3 months later, they come back as a foursome pitching me a company. And so for the purpose of this, I think what was important to me was the initiative that I saw Charlie and Michael take in that moment to go and make something happen. That was actually really all I needed to see. from a team capacity perspective, to go and convince Tim and Yet that they had some ideas, that they should merge their ideas and start a company together. That initiative was great to see.
Thank you. That I'm sure that story was really instructive for others. That I've certainly heard variations of things like that before, so it's good to hear. What about you, Soren?
Well, I think it turns out that Dave and I have been running around the same circles here in the Boston area for 20 years. We never really met in person, but I think I look back at some of my emails and you looked at yours. Like, where did we actually cross paths? So I found out that I participated in the Ignite Clean Energy Prize in 2006 or so, and I think you were managing that, or you were part of that. We didn't meet, like I said, in person, but yeah, I had been around here for a while. I was doing my master's and doing all these things that you were doing here today, participating in the events, pitching, and all that stuff. And so I always knew of Clean Energy Ventures as the group. I think it was the group at the time, right? As the angel group that was always investing in clean energy. And so it was always in the back of my mind. And eventually, when I don't think I pitched the first company, Promethean, to CEVG, but I knew people there. And then when I started Transera, I actually asked for a CEVG member, Mitch Tyson, to join my board because he was familiar with the technology that I was building. And so, I started making those connections early on. And then when we were ready to raise money, we went and pitched to CEV and CEVG. There's a long story here, but I'll try to make it short. The first time around, we couldn't get them to invest in us. It just wasn't the right market. It wasn't the right time. And with some pretty hard feedback, similar to your story, where CEV's like, hey, you guys need to sort this out, take care of this, take care of that. And then we came back a couple of years later with a renewed market and more progress. And sure enough, it worked out this time. So in summary, it takes a long time. You build these relationships over many, many years. If you have the luxury to do that, that's great. Or at least, a couple of conversations, but these are not just overnight events. So that's.
Yeah. I mean, I think the lesson is it's a small climate tech community. And I think these days we need to stick with each other even more than ever. But especially in this geographic region and MIT community and Northeast region, but climate tech overall, it's a small community, and I think what's interesting to note is we at least had heard of each other or knew of each other through different organizations, right? So as a Clean Energy Venture Group, which is different from the fund, which I'm at now. He was at Promethean, which is different from his company. So completely different organizations, but we got to know of each other. And, I knew the name Soren, and, I had heard, he's a really good guy. He's a good CEO, active in the ecosystem. So there was like a positive, feeling, right? So then when we met each other through, pitching Transera, there was already something to build on, right? There was already kind of a positive aspect to the relationship. It wasn't like, cold, who is this person? And I think that's important. I mean, like more than anything else, like we invest in teams and having faith in the team. And of course, Mitch's relationship was very important because Mitch was, our key partner of Clean Energy Venture Group, and Mitch having invested in being on the board, again, cementing that relationship even further. That was important. And then also kind of the experience of so even with Transera, I mean, the first note we had was from 2019, when another member of our group was kind of evaluating the technology and said, hey, this looks interesting. And then 2021 is when we went into formal diligence the first time. And again, really positive about Soren and the team, but we felt like, there were certain aspects of the company that were immature at the time. And we felt were a little bit too risky. And, we gave some feedback and came back, a few years later, having addressed the risks that we had mentioned. And that's always a great sign. And so then this time when we went through the diligence process, it was successful. So I think just the whole idea of building relationships over time, responding to feedback, realizing that, in both cases, first interaction doesn't have to automatically lead to an investment, but can build something that can lead into an investment later on.
Amazing. And a lot to learn. I mean, it's very, very similar sort of ideas there where, a first time no, as long as you listen to feedback, might result in a yes later on. So you've had this first interaction, and clearly there were many, many interactions prior to the decision to, maybe invest. But there's a lot that goes into that actual decision of, yes, we're both excited about each other and we will sort of move forward. And so can you share with some of the folks here, what were some of the important questions that you really dug into? And maybe we'll start with you, David, this time. What were your questions that you wanted to hear from Serena and the team?
Yeah. So, I mean, when we're looking at any company, the most important thing is team. Right. And so I think, just building upon that last answer, having an existing relationship and having the connection through Mitch, and, so that already, put us at a in a positive frame of mind. And then the other things that we look at are, sustainable competitive advantage, right? What can this company do better or different than anyone else? What's unique? What gives them a competitive advantage today and will enable them to maintain a competitive advantage in a large market, win that market, generate a strong exit. And so that's something that we dig in to a very large degree. For us, climate impact is a critical metric. We have a specific metric of 2.5 gigaton emission reduction by 2050. And so, when we're first screening a company, we have a screening tool where we just look at unit emissions and scaling capability. And as we dig into diligence, we dig into both aspects of that. And we have folks on our team that, kind of that's their focus, like, can it meet our emission reduction criteria? So that's something like even from the very first conversation, because there are a lot of companies that are really good companies that just don't reach that scale. And then, yeah, I mean, understanding the exit, like what's the expected value of this investment? What's the potential home run? Like, we want to know, is there a potential of a home run? What's the risk? What's the chance any investment that we make as an early stage investor could go to zero? Is that chance really high in this case? Is it relatively low in this case? And so what's the expected value of this investment? So trying to understand, what's the home run case? What's the floor? What are the risks? And what do we expect as a return on investment? What's the time frame? Who's going to buy the company? Why are they going to buy the company? How are they going to value the company? So these are all, kind of gating criteria that even in the first conversation, we want to have some sense of.
So maybe I can offer the other side of it. Just sorry to take too much, but while they're doing diligence on us, we're also doing some diligence on them too. I mean, this is a really important relationship. So you want to understand who you're getting into that relationship with. What's their reputation in the investment community. So us founders also talk to each other, and we know the investors that are not as friendly to founders, or the investors that have done some terrible things to their founders and things like that. So yeah, no, there is a sort of I would say a very conscious effort from our side to understand the investors. And for example, in my case, we make HVAC systems, air conditioning systems, large metal boxes, deep hardware, I call it, with some material science associated with it. So honestly, I talked to over 100 investors, and only a small fraction of those investors actually understood our technology or appreciated the kind of technology that we're developing. So, it was pretty early on. We knew that CEV had this deep technology and the ability to understand it and do the due diligence on it and really appreciate it. So, it's one of the factors that helped us choose CEV. And so, yeah, I think it's very. I would love to hear Michael's take on it. But yeah, we also have to be fully aware what that relationship is. It matters a lot, and how we run the company. How reasonable would the investors be on a board? Would they accept sometimes the twists and turns of the startup and all of that? So anyway.
So I'm going to push you a little bit on that because you said how important it was and how you were doing diligence, but what questions did you ask that helped you make up your mind?
I mean, I think one of the simple questions is like, do they really understand what we're doing? I spoke with so many investors that just kind of gave it a very brief look, and it was clear that they wouldn't get it. And they wanted to get into more diligence with us, but in some cases I pulled back. I said, I don't think you really understand this, so I don't think it's worth our time. So yeah, no, I really pursued the ones that I thought had the wherewithal to understand it. Oftentimes you see investors that have teams of PhDs in their teams or PhDs in their teams to understand the technologies. I found that as a very positive sign. They do a lot of research themselves. So I don't know if the engine has a research team or not, but there's a lot of market research and technology research. And so for me, it was that kind of like, do they really understand, or they're just kind of, honestly, there are a lot of climate tech funds that sort of popped up overnight in the last couple of years that were, somewhat smaller funds that didn't really have very deep technology or very deep understanding of the space. And it was pretty evident to me early on.
So Michael, was it all about understanding the technology for you as well?
I mean, I would definitely reiterate a lot of what Soren said, but maybe a different angle that I think really struck me with working with Mike and the engine is we sat down with you and Katie and had a kind of, we called it the pre-marriage counseling for founders. But I thought that was pretty emblematic of them really investing and trying to understand Charlie and my dynamic as co-founders who are going to be running the company, and that personal relationship for us. But that's also kind of carried through with, it's not just, I mean, there is the technical support and everything, but in tough tech, it's a team sport. You have to wear a ton of different hats and pull on a bunch of different resources. And I thought that was one example of they are investing in us and also thinking through kind of as we've now grown and matured and tried to confronting a bunch of different questions, helping us think through and see a lot of those. So I think more so than anything I asked, it was more the time and like they invested into getting to know us. That probably was a bigger signal than any question I could have asked, and kind of reading where are the investors spending their time and effort as they diligence you? Is it on multiple facets, or is it just jumping to an economics or something?
I've never heard that term pre-marriage counseling applying to this relationship, but it makes a ton of sense. Is that something that you guys always do as a best practice?
Yeah, maybe I wouldn't call it that. But I think that the relationship at its core, we are embarking, it's the beginning of a relationship that's going to be decadal in length with success. And so that is critical. And so we do try to develop that relationship with all of our founders. I think just the part of that is, just to add to what Dave said earlier, I agree with on team and all of the different components of what we look at, but the actual plan, like the experimentation plan that we're underwriting when we finance a company, and Michael, I think would attest that like we do a lot of that work up front, and it doesn't stop. Like we have the same conversation, just multiple, like kind of downfield now, that we did when we were doing diligence, as if we were already building the company. And that's part of that development, the relationship development. So for us, it was, okay, we have a great team, 2 HBS MBA Wildcatters meeting 2 MIT faculty technology wizards, and they're going to be put together, and we've got to decide what are we doing with the capital that we're raising. How is it going to de-risk the set of things that need to be de-risked over time, focus on, and how do we prioritize those things? I mean, that was probably the bulk of the relationship prior to the fundraise, and then and remains so, I would say. And in order to have those clear, honest conversations about that prioritization and what matters, I think you have to have a grounding in a relationship that's pretty close.
Okay, so we've pitched, we've decided to move forward, we've had our pre-marriage counseling, so now we're married. And so sometimes, startups and the founders and the investors don't always necessarily agree on the path forward. So maybe, Serene, can I ask you to think of a time when maybe you didn't see exactly eye to eye with your investors, and what did you do? How did you work through that?
Yeah, that's interesting. I think we have a number of investors, but I'll focus on the relationship here with CV.
That will make it more interesting for us.
Yeah.
Thank you.
I think one of the things that Dave said early on that stuck with me, he said, don't ever surprise us with stuff. Tell us all the bad things that happen. Of course, you can talk about the good things, but we'd rather know about the bad things because we're here to help. So I took that to heart. Like if anything happens, I would, let them know within a couple of days, like, hey, this thing fell through, or, we had this, not so great conversation with customer X and all of that. So I think that part of we want to keep that really open relationship, and, they're in for the ride with us. And if things don't go as well, which often they don't always go as planned, they should know, they should carry the burden with us and help us through it, and they often do. And in this case, it's helped out really well for us to just be upfront with it. So I don't know if I answer your question, but
Maybe I can turn the tables now, and if you find that a startup is disagreeing with you, and you trust the founders because of course you've selected the team and you believe in them, how do you move forward with that?
Well, it's a good question. So, I mean, so this is a relatively new relationship, right? We invested relatively recently, so I would say we haven't had any significant disagreements yet. I mean, sometimes it happens. But yes, I mean, sometimes yes, I mean, we've certainly had instances where founders haven't told us, things that went wrong, and that's something that we really have a problem with because, again, like we're in a marriage, right? You need communication, and we can't help if we don't know what's going on. And even worse, like, if we're out in the world trying to help fundraise for a company and we're saying things that aren't fully up to date or accurate, right? So that's not a good situation. So, I mean, ultimately, in the worst case, if something like that is ongoing or there's just a fundamental disagreement, ultimately the CEO works for the board. And if there's a fundamental disagreement between the board and the CEO, then you have to think about, okay, is this the right relationship? And do we need to find, move the CEO maybe into another role in the company and find another CEO. So that does happen if there's just a fundamental disagreement that can't be managed. But I think when you have open communication, like Serene was talking about, that's much less likely to happen.
That's good advice. And so how do we keep that open communication? Maybe Michael and Mike.
I mean, I think we're constantly talking. I mean, we talk every 2 weeks with like scheduled meetings, and then there's, impromptu conversations in between. I think a lot of times what at least I personally run up against is like a depth versus breadth kind of dichotomy, where Mike has seen a ton of companies scale and grow and has a lot of valuable experience on like what are these value inflection drivers, and then helping to set these goalposts for the company to get to. And then I'm often approaching it from a grounds up basis of like, well, to do that, I need to do X, Y, and Z. And so it's this balancing, I think, of any disagreements aren't on like, hey, the North Star for our company is extremely clear. We all know where we want to go. And now it's a matter of like, what's the best path to get there? And so I think that's at times where we're maybe to the communication point, talking at different planes, or trying to understand that I haven't communicated clearly enough. What are the hurdles that I'm seeing to get there? That why that milestone may be tougher to achieve, or we need to reallocate resources to get there. And conversely, maybe I'm thinking from my perspective, I don't understand the value inflection driver that future investors will see by achieving a certain milestone, so I'm not prioritizing it appropriately. And so that's kind of the balance that we're usually trying to strike.
So, so communication is certainly one important aspect of the relationship. We have a lot of founders in the room, and two incredible founders that you guys have a lot of belief in. Maybe, Mike, can I ask what's one thing about Michael that you think was sort of a standout aspect of him as a founder that you think would be inspirational to some of these folks here?
Yeah. So I think I want to eventually get back to what.
Let's start there then.
Michael's
Let's
point,
start there.
I think this give and this push and pull is core to the relationship. And on my side, to answer your question, the tenacity of Michael and Charlie as founders, there's not a wall that I'm worried about them breaking down. They're going to break them all down. So that's the thing. I can't pose a question and them not have an answer that is verifiable. They will, and if they don't, they'll go do the work and come back with it. And so that is, I think, the part that's most, I think, interesting about Charlie and Michael. Now, to the push and pull, the other dimension I would add to breadth and depth is time horizon, right? So thinking, what are you doing now and how does that set you up for the long term? As an investor, it's very easy because I'm not in the shoes to be I hear you that we've got to do X, Y, and Z in the next month. Totally got it. I care less about that. I trust because of your tenacity, you're going to go do that. I care about how are we thinking about 2 years, 4 years, 6 years, because that's the time horizon that I'm imagining impact from this company. And I think it's a healthy push and pull, and when it's done right. But to your question, the whole premise of the company and our investment is the tenacity that these two have to be able to go and push through the first month or two, but then also the confidence that the 5-year looks really good.
And David, you've said repeatedly that Serene and team were kind of one of the main reasons that you invested. So what is it about Serene that you think that these folks should look up to?
Yeah, well, I mean, tenacity is a key. I mean, look, right? I mean, I mentioned, 2019, 2021, 20, right? So it's not like Serene got negative feedback and went away. He got the feedback, incorporated, and came back better, and then came back better again. So yeah, I mean, tenacity is absolutely key. I think, again, as a team, especially in technology field, just raw horsepower, being smart, but being smart in a smart way. Both technology and market are really important. Also for us, alignment is really important. Just like we're going after, the same thing as far as, making a difference with respect to climate change and making the world a better place and ethics. I mean, that's just non-negotiable for us. And again, is something we felt extremely good about with Serene. And then one other dimension, which I think experienced CEOs are better in because it's hard. It might seem simple, but it's kind of a dimension of how folks respond to feedback, because there's two ends of the spectrum, right? I mean, so, on one end, you could have a CEO who just, has a very clear idea of what they're doing and they're going to do it. And you could give them suggestions and it kind of goes in one ear at the other, and they're going to do what they think they want, right? They know what to do. And we've seen this in probably more often in younger CEOs, who, everything they've done in life to that point, they've succeeded at. And so they're going to succeed at this, right? And they know what to do. And in those cases, we say, great, you already know what to do. You don't need us. right? Like if our feedback isn't going to make a difference, then, you know, it doesn't really make sense for us to invest because like we're looking for an interactive relationship. So that's kind of one end of the spectrum. The other end of the spectrum, and again, you know, we've probably seen this again more often in younger CEOs where someone is, you know, like a sponge and is great and they listen to everything. But it's almost like they don't have their own ideas, right? You know, so they're only responding to feedback, and there's kind of like just a reflection of us rather than kind of bringing their own ideas, and that's not great either. So finding that balance, it's not easy, but finding that balance. So like experienced CEOs like Serene, like is really great at listening, understanding the feedback, and then coming back with his own ideas that, you know, reflects an understanding of the feedback, but reflects also his own expertise and his own experience and his team's experience, and coming up with kind of like a result that's better than one perspective by itself.
What great advice to the folks in the room here. So I think guys, we've got some time now to answer a few of your questions, and this is your opportunity to get the real deal here with some of the real gossip of what happens between startups and investors. So you know, bring it on. Let's get some really tough questions. And I don't know if we have a mic to go around the room. Oh, we're going to steal one of ours. Excellent.
Great. Okay.
Hey guys, one question that I had is, as a very early stage startup, which I think a lot of us here are, how do you think about phasing of when you start bringing things to VCs? Because I think one of the things that we found is VCs often love to pass even before you have maybe even incorporated the company. And so how do you think through when something is actually ready? Maybe you have like a set of friendly VCs that you talk to early, but how do you think through when it's ready to start bridging with other VCs and how to phase that?
Quickly, from if you're, you know, students right now, like getting a deal done requires urgency and a deadline. And I guess, like, for better or worse, Charlie and I had a deadline. If we didn't have salaries by a certain point, like, the venture was going to die, and we were going to, you know, and we had like a realistic timeline, and we were very transparent with each other on how long that was. But I would say the thing is, like, create urgency. There's like, it needs to get done. And so, like, that is motivation for you, but you also let the VCs know that, like, hey, if you tell us to pass for 6 months, like, this opportunity isn't coming back around. So there's different ways to do that. But if you're currently a student and you're like, hey, I need to pay myself a salary, like, I don't have forever here, like, I don't know. For me, that was one of the things, whether that's the best mechanism or if there's something else, but that's a piece.
So there's a way to approach investors in looking for like a mentoring relationship and like being like clear, like, hey, you know, I don't know if we're ready for you to invest tomorrow, but we want to learn from you, and we think we have something we want to learn from you. So like, let me just say quickly. So like there's two organizations that I've talked about: Clean Energy Venture Group. So that's an angel investment group, 35 partners, one of which is Mitch Tyson, who Serene mentioned. So Clean Energy Venture Group, like the partners are almost all like recovering entrepreneurs of one type or another, right? And so they've been through those experiences. They love to mentor. And so if you come to Clean Energy Venture Group and say, hey, you know, I'm really committed to doing something great. I have some ideas. Can you help me refine it? There's often you can find folks who are just willing to help you and to help mentor the idea. And that's happened in many circumstances. And you know, we in CEV kind of had that same mindset and kind of have a partnership, and we look for those companies that are looking for mentoring. So there's certainly kind of an on-ramp when you have something and you're very genuine and you're willing to be, you know, have that tenacity, but you're also open to feedback, where you can develop a mentoring relationship early on.
Yeah, Ian, and I would just add, like, I think this community has so much going, like, there's so much there for you, inclusive of, but not limited to VCs, right? I think it can be one input into your calculus. It should not be the only one. So all of the that you do in the CEP, that's awesome. There are other programs you can do, other accelerators you can join that all kind of feed in this input as a function of, that is your startup, that then you can take all that, convert it into knowledge and decide what to do with it. Some of that will be investors who are telling you no, some of them are going to work with you, and you'll get a sense for that pretty quickly, if they're willing to actually be mentor and have the operating experience to help you do that. But I would take a broader approach to the ecosystem, not just investors. They don't know everything.
Yeah, I was just going to add, my journey was a little different. I didn't talk to investors for the first couple of years. Only I didn't pitch to them. I mean, my first thing I did was I went and got some government grants and local state grants. Massachusetts Clean Energy Center is a real big supporter. I participated in competitions, got some prizes. So I scrounged up enough funding to try a few things before I go and talk to and pitch to investors the idea. But what I did do was what David is saying is I started building these relationships with the mentors and other investors like Mitch Tyson, Jim Matheson, who many of you know teaches the TTV class at HBS. I got him as an advisor. So I sort of started creating that sphere of mentors and advisors, which then would introduce me to investors, and then when it was the right time to pitch. So it took a couple of years for me before I actually pitched something, but I was building it from day one.
One more question. Your one opportunity. Hold on, we'll get your mic.
Thank you. So you mentioned government grants, and especially with the recent administration and some of the changes. So I'm curious, either as startups or as investors, for especially the students in the room, any words of encouragement or optimism or positivity that you're seeing as we look out for the next couple of years? Thanks.
Yeah, I was just going to mention that. It's a new world out there now, right? In the last couple of months. We do have some grants that have been delayed. Personally, I don't think they're going to be canceled. I think this work is really necessary. This is some of the funding that's been allocated for 5-10 years. So I think it's just a matter of time while things are being reworked. That's a bit more optimist. I'm sure others might think there might not be as optimistic, but I think the government does play a key role in our climate tech in our industry. I'm very encouraged to see local state grants like Massachusetts Clean Energy Center. That's not affected by any of this federal stuff. In fact, we just got a grant recently to do a pilot with a customer. So yeah, those are available. I think you should not discount them. And maybe, I hope it's just a matter of time before things. What do you think?
Yeah, no, I agree. I mean, look, I mean, we think in like 30-year time frames for when we need to mitigate climate change. You know, we're likely to have a new Congress in less than 2 years. So, you know, hopefully this will be a relative blip. And yes, we are very fortunate to be living in Massachusetts, because Massachusetts absolutely is continuing to support climate tech.
I think the work is more important today than it was, like the work that you all are doing and should continue to do, because if you're starting a company today, you're going to be commercial well beyond 4 years from now, right? And that's the game that you're playing. There's capital out there for you. I think that the capital markets are pulling back a bit. There's a lot of capital out there though. And so they're going to have to start spending in this time period. And I think that's a good thing if you're going out to raise money. I think particularly after we get through the chaos of probably the first 6 months in this administration.
Like the end goal doesn't change. You're going to go for like climate solutions to scale and win. They need to win on price and like having a baked in green premium. So it's just making you grow up faster. Like, but that doesn't change like what you're doing when you're doing. Like, I think maybe the bright side of this is it forces you to look hard in the mirror and face some harsh realities about what is the realistic way to scale and grow your company. And so like that is like the sooner you can take that on and build it into your plans, the better.
Well, thank you all so much for letting us chat with you guys and telling you a little bit about the investor and founder relations. I hope that was a little bit enlightening for you. And let me pass it back to Alejandro. Thank you.
Please help me thank the panelists. And yes, we're gonna have lunch right outside, and please come back around 12:40. We're gonna get things started around then. Thank you. Thank you so much.
Hello, everyone. Welcome back. I hope you all enjoyed Café Luna. Those sandwiches are usually really good. My name is Gabriel. I am one of the co-managing directors, and it's my pleasure to start now our third block of startups. We have some fantastic people that are going to join us soon, and we'll kick it off with the team from Solvanic. So the floor is yours.
Awesome. So we're Solvanic, and we're enabling flexible carbon capture for the energy transition. Looking at projections by the IPCC and other international agencies, there's a clear and pressing need to decarbonize our society. Even in the best case scenarios, to avoid the worst effects of climate change, we need to hit net zero emissions by 2100 at latest. This will require a fundamental shift in most of what we do as a society, both building out new electrified infrastructure to make use of renewables and decarbonizing our existing infrastructure. Point source emissions in the United States accounted for over half of our greenhouse gas emissions in 2023, with around 2/3 of that coming from power generation and the balance primarily heavy industry. Power generation from coal and natural gas are considered hard to abate sectors due to the need for steady, reliable baseload and the ability to ramp production up and down in response to fluctuations in demand. While renewable energy can meaningfully offset these emissions, due to these restrictions, this sector is considered hard to fully abate. At the same time, commodity production such as cement, metals, and chemicals are also considered hard to abate activities due to the need for vast amounts of heat and reactions that intrinsically release CO2. Point of emission carbon capture and sequestration is a strategy for mitigating the emissions of these existing infrastructures, separating and storing the CO2 underground to avoid the climate impacts. That said, existing thermal carbon capture systems are not sufficient. They're energy intensive, they require extensive thermal integration with lengthy downtimes and expensive retrofits. They're only projected to be economically viable for very large systems exceeding 1 megaton per year. And they have sluggish thermal responses, making them incurring additional costs in the new critical application of load-following natural gas plants, which will increase in prevalence as we add more renewables to the grid. Our electrochemical carbon capture technology addresses all these challenges. We're much more energy efficient, coming in at 50% of the baseline energy expenditure for the industry baseline MEA process. We enable drop-in retrofits that are compatible with renewable electricity. The modularity of our electrochemical cells enables flexible scaling across process applications. And the rapid responses make them much more dynamically suited to the new grid. Both our tech and the state-of-the-art use sorbents, whereby we have a mixed flue gas coming in and we're selectively binding the CO2. In a traditional thermally mediated separation, we would then heat the entire solution to break these bonds and release a pure stream for sequestration. The trick we do is we use this competitive binding mechanism whereby the introduction of copper ions will isothermally release the CO2. So by electrochemically plating and stripping this copper, we can enable a fully continuous flow process, capturing with copper lean solutions and releasing from copper-rich solutions. This allows us to use the existing amine absorption tech with a new innovative electrochemical regeneration step. This was developed extensively at MIT, explored in over 12 publications, and protected by 7 patents. Looking at the current market, there's a clear industry preference for these thermal amine systems, representing 90% of currently installed capacity and over 2/3 of announced future projects. There are other electrochemical competitors entering the space, hoping to capitalize on the same advantages we just discussed. However, they're imagining a ground-up redesign of the entire system, requiring much more expensive de-risking. The Solvanic technology finds the best of both these worlds, pairing the electrochemical efficiency with the reliability of the industry-preferred amine process. We use this established amine absorption, meaning that our tech is half de-risked off the bat with a potential 30% reduction in capital expenditure due to our different chemistry. We also tap into existing robust supply chains using off-the-shelf commodity chemicals. There's no need to worry about sourcing expensive ion exchange membranes, precious metals, or custom organic molecules like our competitors. This leaves us poised for rapid scaling and adoption.
Thanks, Mike. We will provide our flexible and modular carbon capture approach across the power generation and heavy industry sectors. That lends itself to a few different revenue sources. First and foremost, by providing CO2 separations in existing markets, such as hydrogen and ammonia production. Second, by offering a decarbonization solution to customers looking to take advantage of tax incentives or the need to comply with local emissions regulations. And last, by entering the voluntary low carbon electricity market and helping electricity consumers meet their net zero pledges. Our technology has the potential to address a $22 billion domestic market. Looking at the distribution of emitters across the United States, we see that there are a large number of mid-scale power plants that currently operate without an economical carbon capture solution, representing about 180 million tons per annum of CO2 that is emitted unabated. Adding relevant heavy industrial emitters into that range yields a 450 million ton per annum CO2 emissions. And looking at all direct emitters across the United States, that number balloons out to over 2.2 gigatons of unabated CO2 emissions. Attaching a $10 royalty to the capture and sequestration of those emissions yields approximately a $2, $4, and $22 billion market in just the US. Initially, we'll focus on customers in the Texas and Louisiana region, as there's a high density of mid-scale emitters there, but also existing infrastructure to support carbon dioxide sequestration. One early customer of note is the micro LNG producer. They require CO2 capture at typically less than 1 million ton per annum from two distinct streams. That is, removal of CO2 from flue gas associated with power generation and removal of CO2 from natural gas prior to its liquefaction and export. We're currently engaged or about to engage in a FEED study with one such micro LNG producer to assess our technology across both of these applications. And engaging with these early adopters is critical to demonstrate the versatility of our technology and help us de-risk and scale into both of these industries. So where are we now? So far, we have a patented and demonstrated concept that is operated in the laboratory for 200 hours at a scale of roughly 50 grams per day. From there, we'll work through a scaled prototype and field prototype to pilot by 2031, where we'll be operating at 500 tons of CO2 per day, or equivalent to roughly 0.2 million tons of CO2 per annum. This is where we'll be able to pull in first royalties from those mid-scale emitters, mid-scale power and industrial emitting customers. Beyond that, we'll enter more typical commercial operations, where by 2035, we'll be consuming capturing in the order of 5,000 tons per day, where we can offer a drop-in solution for large, heavy industrial emitters across the United States or globally. So our core team is myself, Mike, and Professor Alan Hatton, all presently at MIT. We bring over 25 years of climate research, 50 years of engineering, and with Alan specifically over 5 years of startup experience with previous climate startups out of his lab, Verdox and Mantle. We're also advised by Glenn Wilson, who's giving us advice on the CO2 monetization and sequestration side of things. Thank you very much. Happy to take any questions.
Thank you. Can you speak a little bit? So that slide that you saw, that you showed kind of the pathway to 0.2 megatons per annum. Can you talk a little bit about like the key milestones and how you think, the one you just passed, like the key milestones and then how do you think about scale effects from a cost perspective? I know at least in a lot of these kind of solutions for CCUS, like even as they scaled, the cost has not really improved by much, but just how do you think about that from an advantage for you?
So we're hoping to develop basically a baseline modular electrochemical cell with these early demonstrations. And the idea would be to achieve economies of scale in production with the subcontractors that be producing those. So once we have this demonstrated in 2027 or so, 2029, we then have a modular electrochemical solution that we can continue expanding to those other applications.
And if you think about that timeline, like is it the technology that's the bottleneck to try to get it to the next level? Is it people? Is it like, what is it? Money, funding?
So we've benchmarked this timeline against other carbon capture startups like Mantle and Savante. We're in this sweet spot where we can leverage the existing amine infrastructure and also take some of the knowledge and experience from other electrochemical industries. So we could conceivably scale more quickly than this. We're being maybe slightly conservative in this estimate, but it is quite a large jump from, say, our current operations to the next step, which is 10,000 times multiple. Yeah.
Yeah, thank you. You mentioned 45Q and tax credits and the revenue streams. How dependent is your business model, at least in the short term, with regard to that? And in the case parts of the IRA is repealed, what's your mitigation plan?
So I mentioned 3 different revenue sources. First and foremost is by providing CO2 separations at a lower cost in existing markets. So hydrogen, ammonia, methanol, regular chemical purification steps. So we're somewhat insensitive to the 45Q from that perspective. Ideally, we want to decarbonize power generation and make the largest climate impact that we can. And part of that might be by entering the voluntary carbon market as the prices come up. But we want to start initially in the existing CO2 separation space.
If I can, oh yeah. Oops, if I can add, there are also opportunities to expand internationally. There's a more robust carbon market in Europe that doesn't show any signs of subsiding. Mantle has a current pilot demonstration coming online in Canada soon. So like even if there's regulatory uncertainty in the United States, there are potential other markets globally we can enter.
Thank you. And maybe a follow-up question still on business model. Are you licensing your technology to emitters, or are you, in the case of credits, for instance, you mentioned that, are you owning that and selling that on markets, or are you sharing the profits with your clients?
And we would typically be operating asset light, so not owning or operating the facility. They would be collecting the credit. We would be earning a royalty based on the throughput of CO2 from that installation.
I'm curious you kind of have your 2x2 where you were benchmarking yourself against others. There's a lot more that kind of goes into it than just, obviously, there's many other metrics. I'm just wondering, just pushing on a few, I'm going to say maybe the footprint and maybe the kind of feedstock impurities, but also I'm curious on what other kind of metrics that you think you win on or need to improve on, if that makes sense, versus the competition.
So one of the biggest ones I want to address is the economies of scale. There's a lot more that goes into this than we could easily get through in the slides. One of the biggest advantages of this tech is that we can actually desorb at high pressure, going up to as high as 20 bar. Compressors to get that CO2 up to like 150 bar to sequester is one of the things that scales down the worst, with like the scaling exponent being like 0.4-ish. So being able to offload that onto a modular electrochemical cell that's insensitive to scale and avoiding the components that really kill you as you move down makes this much more attractive proposition for those smaller emitters.
And on the feedstock and the input side, I mean, I'm curious, I mean, anything sulfurous is going to be detrimental, I'm sure, to a copper-based system, but I don't know if that gets scrubbed out in advance.
Yeah, the idea would be to operate downstream of the typical SOx NOx removal units. One thing is that our tech is a little bit less sensitive. Well, we haven't, so that's one of the things that we're looking to scale up and address is just get more person hours at the problem. But sort of qualitatively, we expect to be less sensitive to that than people relying on like single catalyst sites with precious metals. Because if you lose one of those, it's a huge deal. If we're continuously plating and stripping and refreshing that copper, there's potential more ways, strategies that you can use to recover that.
And then I guess one more on that as well as the electricity cost that you're actually going to, or the electricity you're going to need. How do you think about that in some of these early implementations where you're going to need that electricity source, unlike a heat source that might be more readily available?
So for power generators, we'd be tapping directly into the power that they're generating. So in order to buffer out like transient effects, if you're doing load following, you could plug directly into the grid. All the TEAs that we did were very conservative with the electricity cost. Like one of the biggest complaints that VCs tend to have is that a lot of these companies assume like a penny per kilowatt hour. Like we're assuming very industry standard electricity costs and still comes out competitive. So just for like a benchmark, we expect nominal energetics on the order of 1.25 gigajoules per ton. That would be like 0.8-ish for the electrochemical desorption, the balance being the sequestration and storage. compression and sequestration. And that's relatively insensitive to the actual feed concentration. So that's another key factor where, natural gas power plants become a lot more dilute. It's like 4% CO2 compared to coal, which is like 15. And that's where the traditional thermal scrubbing systems really struggle. But we're actually relatively, because of how the losses actually come about in our system, we're much more insensitive to the actual concentration in that feed.
How sensitive are you to projections for copper demand by, say, 2031 when you're sort of starting to scale up to these larger sizes?
Yeah, that's a good question. So I think the typical 500 megawatt power plant, we have this from our techno-economic analysis, would consume much less than, say, 1% of the global production of copper as it stands today. So we don't see that being a significant issue as we really scale up to meet the carbon capture demand. But it's certainly a consideration. Copper is a reasonable portion of our CapEx.
Maybe another question about carbon footprint. How do you make sure that including the power input into the system, that your life cycle carbon footprint remains net zero or net negative?
So so say from a post-combustion power plant, we'll be capturing 90 to 95% of those emissions. So we'll never be net negative, but avoiding as much CO2 as we can. And then we're not sure yet as to what the supply chains look like, or the carbon intensity of the supply chains look like for a lot of our commodities yet. That's work we have to do.
If there's really that much more of a desire for carbon negative solutions, we can also plug into BECCS.
Great.
Thank you very much. And now up next, we have Solid Sky.
Can everyone hear me okay? Great. Hi, everyone. So my name is Aiden. I spent 2 years running a Department of Energy commercialization programs, helping startups get technologies out of federal labs. And today I'm going to tell you how I'm doing the same thing with Solid Sky. So this is an ethane cracker. All it does is it takes ethane gas, exposes it to really high temperatures, around 1700 C, and in the process it cracks, loses hydrogen, becomes double bonded ethylene. Each one of these facilities, there's only so many of them, will make around 1 million tons a year worth of ethylene, and it will also make over 2 million tons of CO2 as well. So being able to decarbonize this is a huge challenge for the chemical sector. And it's a huge challenge for a few reasons. Main reason is that by volume, it's making around 5% of US CO2 emissions every single year, all of those facilities. It's also a high value commodity, but a high volume commodity as well. We're making around 85 million tons, 5% growth year on year on year for at least the next decade. And we've invested almost $200 billion in the infrastructure to make this chemical up to this point. And the main challenge I want to talk about today is that a lot of the conventional ways of trying to decarbonize this sector, whether you're talking about carbon capture and storage, or you're talking about electrochemical methods of making ethylene, have extremely uncertain return profiles. And this was found across interviews with around 50 different stakeholders at players all over the petrochemical space, and the conclusion from them was the same. Currently, clean tech is too expensive to actually deploy. They know carbon management is coming. They know they're going to have to do it soon, but they want it to be on their terms. They want it to be profitable, and they want it to be as low risk as is feasible. So the whole thesis that I'm talking about today is that we need a way of turning CO2 to value in a way that's going to increase profits. It's going to drive its own adoption regardless of policy mechanism, and it's going to take advantage of the infrastructure we already have today. So we're working on this with the Lawrence Berkeley Energy Lab out of California. They have a novel catalyst that can take CO2 and use it as what's called a soft oxidant. It just means that the ethane is more likely to give up its hydrogen to turn into ethylene. Now, what's great about this is that it has basically no byproducts in the reaction itself. It's built on well-established, well-known thermochemical technologies, which means that it can scale faster and way more predictably. And it's our intention to basically take this reactor, have an electric heating component with it because the reaction temperature at 500 C is much lower, and then retrofit it into the legacy ethane crackers that we already have today that need to be decarbonized as fast as possible. In terms of how much less energy, it's a wide range of different technologies to compare against. The main ones I want to talk about are conventional steam cracking, 86% less energy. That works out in an energy OPEX to a savings of about $100 per ton, which on $980 per ton current market price is pretty decent. And when you compare it to other methods of making things electrochemically, it's much broader because there's two main camps of doing this electrochemically, but it's anywhere from 2 to 200 times cheaper from an energy perspective to make this product this way. And what that means is that if you look at an average facility implementation, this was a model that we did, assuming 40% of the CO2 is being captured and utilized because you can't do 100% of it. Margins improved by well over 30%, profitability increases by around $38 million a year, driven by a significant energy decrease. You avoid over 1 million tons per year of CO2 emissions directly. You could get additional revenue of around $42 million in carbon credits. Whether or not that would be realized by the voluntary market is still uncertain at this point. And then you're looking at a pretty significant internal rate of return for what we think is a fair facility installation cost of around $300 million. This is obviously a huge market. We're not going to take on all of it. We intend to focus on the 35 US ethane crackers that exist within our borders that are responsible for all of the emissions that we talked about previously. And we intend to generate revenue through licensing. We think this is a fairly reasonable licensing number. And that speaks to our business model. We intend to actually partner with engineering, procurement, and construction groups. These are the folks that build the facilities that companies like Shell that we would recognize actually operate and derive revenue off of. But we would generate the revenue through licensing with them, and then generate funding primarily via equity and also a strategic investment. Obviously, later stage, you have growth capital, you have debt, all of the other vehicles that may become available. We're still hoping grants will rematerialize at some point, but we've taken them out of our plan in the short term. In terms of how deployment will work, there's a lot of considerations to go into a facility of this size. One of them is obviously you have to make sure that the footprint is considered, the ready access to CO2 flue gas, and also some facilities are sensitive to the ratio between hydrogen and carbon monoxide, which I can talk about later. But that does mean that there are other facilities that could be considered. We are looking at some of those options, but for all of them, the deployment looks exactly the same. You partner with the EPC, you install the modules at these plants, we generate the revenue from the licensing and credits, and the modules will produce products that they can then sell. And given that they are module, you can have as many or as few as you want. You can scale production at any point in time. This is our R&D plan in the really short term. There's a lot of questions we have to answer with the very early stage federal lab technology. That being said, our main focus is going to be on actually optimizing the catalyst, getting relevant models on it, and then hopefully converging to a point where we can have what we would call a maximum virtual product, which is a digital twin of the reactor based on all catalyst data that we can attribute in a fairly short time that just hasn't been done in the initial pass-through. This is our broader timeline here. We already have funding for the first step. It's already happening at Berkeley as of a few weeks ago. And then the catalyst optimization step, as I mentioned, moving into prototype development, deployment validation by finding a pilot partner, and hopefully getting an industry pilot we expect sometime before 2030, although not much more before. This is our traction to dates. We're in the Cradle to Commerce's second accelerator cohort. This is run by the DOE. We completed the engine's blueprint accelerator. We started to build relationships with many of the major petrochemical players I mentioned earlier, and we have secured our first $300,000 in funding, and we're waiting on $13 million worth of grants. How many will or won't be there, I have absolutely no idea, but they're out there. Shouldn't be funny, but yeah. And then I just want to conclude with the excellent team that I have. So I told you a little bit about myself and my background, but I really want to highlight the work of Dr. Joseph Brindle and also Dr. Ji-Hong Lee. They both did their PhDs on either side of the spectrum. Joe's mostly focused on a reaction design, reaction engineering upstream. And Dr. Ji-Hong Lee's done a lot of work with catalysts as well as novel separation technologies. You also have our inventor, Dr. Ji Su, who is our technical advisor. And then we're hoping within the next year, possibly less, to hire a head scientist that has experience in catalysis and scaling in this space, as well as a head of partnerships is what I would call it. But basically, it's someone who understands how to sell, how to deploy, how to network with the very complicated relationships between operators and EPCs. And with that, I just wanted to thank you for your time and attention, and I would love to answer any questions you may have. Thank you.
Thank you so much for the presentation. My question is more on the catalyst itself. Could you elaborate on what it's made of and like if there are any geopolitical or material like supply chain risks with being able to scale that?
Yeah, so currently the catalyst, it's fairly standard. So it's on a zeolite and it's a zinc chromium active site. We don't expect any issues geopolitically. What I do want to highlight, since we're talking about the catalyst, is that we currently have two different problems with those metals. One of them is probably more obvious, which is that chromium may or may not be subject to regulation. We've spoken to some folks who are concerned that the trend in Europe of basically trying to get rid of chromium is going to move to the US. Obviously, that timeline has probably changed with the administration change in the EPA, but probably still inside of the decade. And then zinc, we have a small problem with the zinc where the catalyst is slowly degrading. The zinc is leaching to zinc oxide. So that's two separate problems we have to address. We have a pretty good idea of how we're going to address them. It was actually the subject of a CIBR grant that we are waiting to hear back on. But yeah, no, to answer your question, I wouldn't expect any geopolitical issues, but there are other issues we would have to address.
Thank you.
I'm curious about the retrofit plan. Can you tell us a little bit more about how that plugs in? How does that actually work alongside one of these, you say, 1700 C steam crackers? What does that actually look like?
Yeah. So the way that it would look is you have the steam cracker, and most of the CO2 is coming from the actual methane combustion to get to those really high temperatures, just because there's no feasible way to do it. You have that mixed CO2 stream from flue. Now the challenge here, and this was something that I spoke to earlier, and I think we can actually maybe back up to that slide just to cover it. But basically the challenge is that actually finding the footprint and the way to capture that flue gas, regardless of purity, is a retrofit challenge. But we basically get a hold of that CO2. It's not going to be super poisoned simply because of the nature of the reaction that it's coming from. And then you have what's called a packed bed reactor. It's pretty standard in the industry. It's just catalyst pellets in a very small tube, and you would have these tubes in parallel in a module. The actual more, I would say, more significant logistical challenge would actually be downstream in the actual separations itself. More than likely, they will have the separations infrastructure on site to do so, but it's mostly just ducting. And given how tight the footprint of these facilities can be, it may not be just ducting. I'm not sure if that answered your question.
It does, but so the next step is obviously you've got ethane going in there, and I'm just so it's completely separate to this. It's like a second cracker, effectively alongside it.
Yeah.
So okay. Yeah. As opposed to a retrofit, more a second stream. Then I guess you're channeling the ethane into the standard route and into your route as well.
Yeah, I would think about it like this. You have the mainline process that's still producing a lot of the volume. You have a secondary, much more profitable process that can take some fraction of the blend entirely up to the operator's choice. So there's basically two separate reactors that are achieving the exact same outcome, the exact same identical drop-in product. It's just that you're not actually fully replacing the facility. You are using a lot of the CO2 that it's using to drive a much more profitable process.
Okay, understood. And then I guess, what temperature was your reactor running at, and how were you heating that one? It was 500?
500 to 550 C is the sweet spot roughly within there, and that's low enough that you can do purely electric heating if you wanted, most likely a resistive, just because it's not hard to get it up to that temperature. So we're going to go with basically it's a packed bed with a heating element inside it, which has been shown before and already scaled.
As you think about working towards the first demonstration plant, what are sort of some of the metrics that you believe potential partners or people who are going to be the decision makers for these retrofit sites are going to want to see from your initial demonstration pilot to be able to sort of get to buy-in?
I'm not sure whether all of them will come from the pilot. Some of them may come from further lab testing. I know that the two that seem to come up pretty consistently is of the first pass conversion, because we are a co-reaction technically. So it's CO2 and ethane. It's making CO and ethylene. We only have a 40% single pass conversion right now with the current iteration of the catalyst. So you're basically on the other side having an equal blend of 5 different, very similarly weighted and polarized molecules. That adds to downstream separation costs because, separation is almost entirely thermally intensive, whether you're doing pressure swing, whether you're doing cryogenic, it's all going to be downstream costs. So that's a huge component of it. Whether or not that's proven in a pilot or a lab, I'm less sure on. The second thing that seems to come up pretty consistently is the notion of whether or not you can actually continuously regenerate the catalyst in the way that would be needed so that you're not having to constantly have, the downtime to replace catalysts every single time. Whether or not they're expensive catalyst metals, it's still, I don't want to turn this facility off for any reason. And that would certainly be a pilot conversation, because if you're in the actual pure CO2 blend, argon dilute lab like blend, or humidity upstream or whatever you're changing, you can actually have an answer about how long this catalyst would last and what circumstances would allow us to actually regenerate it in operations.
Can you speak a little bit about the team members you're wanting to recruit, and just like how do you think about their role, and what in a sense are the barriers that you want them to solve?
Yeah. So I would say that currently, what's great about the team that we have right now is that we have people that have a lot of experience in the research side of things, a lot of experience in the actual design and the optimization of systems, either, digital simulated or actual lab work. None of them have actually done this before. They haven't tried to get something from, 50 milliliters a minute to 5 liters to 50 liters and all of the challenges that can come with that. They've seen it in books. They haven't done it yet. So the main first thing I want to address is knowing the challenge of scaling science, someone who has actually scaled ideally in an industrial space before, so that a lot of those unknowns are no longer unknown. Of course, there always will be, but we can try to mitigate. And then the head of partnerships is mostly trying to address the reality that you're dealing with a very intimate relationship between the actual EPC and the operator. Who's the customer? Who's the influencer? They're often the same, and they're very much interchangeable. Plus, you have the long cycle times, you have the red tape, you have the clearance, you have all of these things that are so different from selling to, like a consumer, as an example. So the hope is that they would be able to address a lot of those intricacies and a lot of those uncertainties, and also just grant the legitimacy of saying, hey, I've been building these projects before. I know what you're concerned about. We're not going to break your plan.
Just a question on the 26% IRR that you coded and on one of the slides. Is that from the perspective of the owner operator?
Yeah.
Okay.
Yeah.
And then how much of that is dependent on just their own efficiencies?
That's a good question. So the IRR itself was definitely trying to be as generalized as possible. The way that it was pulled was we were just looking at if you have a certain blend of ethylene, some of it made through process A, some of it made through our process. What is the average increase on the profit margin for that by the decrease in energy? And what's that likely outcome going to lead to in terms of the IRR of the facility?
Thank you.
Great. Now next we have H2.
Hello, everyone. Hi, I'm Ian. I'm the CEO and co-founder of OmniPath H2, and we're working on midstream hydrogen transport solutions to unlock the hydrogen economy. So why do we need a hydrogen economy? We need a hydrogen economy because hydrogen will be critical to decarbonizing around 20% of our emissions, with particularly heavy usage in the industrial sector. This means that we would expect demand for clean hydrogen to increase from essentially nothing today to about 300 million tons in 2050. And as a first step, we already need to replace the 90 million tons of dirty gray hydrogen that's already being used. This is estimated to cost around $15 trillion in global investments into the sector. So if we look at where investment has been going, the vast majority has been going into how do we produce clean hydrogen. And if you look at the market for hydrogen today, you can see why this is the case, because the vast majority is just produced on site with steam methane reforming. If you look at where VC funding has been going, people aren't really working on the storage and transport issue yet. But let's accelerate ahead to 2050. In 2050, clean hydrogen is mostly going to be a merchant market, and about 90% of the currently planned merchant hydrogen projects don't have a buyer because that midstream infrastructure doesn't exist. And about $1.2 trillion in CapEx is going to be needed to build that out. Let's look at this from the perspective of a potential customer. Let's take the Cleveland Cliffs Iron and Steel plant in Ohio. If they wanted to secure hydrogen to decarbonize for their iron production, there's three things they could do. One, they could do on-site steam methane reforming to produce their hydrogen. Two, they could install electrolyzers on site. Or three, they could go do electrolysis in a region with abundant renewables and transport that to their site. They could do steam methane reforming of natural gas. It emits a ton of CO2, so if they want to decarbonize, that's out. If they wanted to do on-site electrolysis, like a lot of folks are currently thinking, they would need double the amount of renewable electricity currently installed in the state of Ohio to do that, which seems unlikely. This leaves them with the option of going to a region with abundant renewables and then transporting that hydrogen to their site. It's the only viable option, but it is prohibitively expensive today, adding somewhere between $2 and $20 per kilogram to the cost. Why is it so expensive to transport hydrogen? It's because there are no good options for transporting hydrogen. There's a couple ways you can do it. You can liquefy it and transport it. That's what folks like NASA are doing. It is incredibly expensive. You can compress it as a gas and then, potentially stick it on the back of a truck. That works at small scales. It doesn't scale up super well with larger volumes or longer distances. You can blend it into natural gas pipelines, but there's a cap to how much you can blend, or you can build new hydrogen pipelines, but this is a massive capex and regulatory undertaking. So what do we want to do? We don't want to transport hydrogen. We want to transport something that we already know how to transport as a society. This is where something like ammonia or a class of molecules called liquid organic hydrogen carriers come in. We already move millions of tons of these around the world as a society each year. And so instead of transporting hydrogen, what we can do is we can bind hydrogen to nitrogen to make ammonia, transport ammonia using existing infrastructure, and then crack that hydrogen back off at the end. The reason that people aren't doing this today is because that final step of hydrogen release is very inefficient.
And that's where our technology comes in. I'm Devin, CTO and co-founder of OmniPath H2. Our catalyst releases the hydrogen from the ammonia or hydrogen carrier, which then gets simultaneously separated and purified by our co-located palladium membrane. This palladium membrane is not simply a physical passive separator, but a catalytically active material in itself. This leads to, by extracting out the hydrogen as it's being produced, we can shift the equilibrium to the right. This improves the round trip efficiency, ultimately reducing the cost of our system, enabling hydrogen carriers such as ammonia to be a solution in a way that simply wasn't possible before. The synergistic effect of our catalyst on the hydrogen release, the separation, and the purification enables a higher hydrogen production rate at a potentially lower operating temperature that still generates high purity hydrogen that can be directly utilized in fuel cells or dropped into downstream conversions.
Thanks, Devin. So we think that we have the best product on the market and under development because we expect to be lower cost, more modular, more scalable, and more flexible than a lot of the other options that are out there. I'm keeping an eye on the time, so I'm going to move on, but ask me questions about that. Let's assume we do have the best technology. How do we bring this to market? You may remember from an earlier slide, I mentioned that the vast majority of these production sites don't have a way to connect with demand. We plan on going to them and offering them the lowest cost option for transporting their hydrogen. That's from our TEA at scale, both for us and for compressed gas at mid scale. And then we'll connect to demand sites with proven willingness to pay in some of our key beachhead sectors, partly driven by regulatory reasons, partly driven by hydrogen being a better solution in things like forklifts. This is a huge market opportunity. If you look at the entire TAM for hydrogen transport, we expect it to be about $50 billion by 2035. And even if you just look at the beachheads we're targeting, we expect that to be $5 billion in 2035 and already in conversations with a lot of potential customers leading in the space. We think that we've pulled together the right team to tackle this. I'm Ian. I'm a second-year MBA student at Harvard with prior experience commercializing technologies at Sila Nanotechnologies. We've got Yogi over here. He's a professor at MIT, the inventor of the technology. Devin, we heard from earlier, CTO, postdoc at Harvard, and we're also supported by Julian and Rui, who are both in Yogi's lab. We also have an advisor, Chalk, from Omia, with a lot of experience scaling technologies similar to this. All right. Well, last slide didn't have that much on it. It's just my email. JK. Please join us on our journey to unlock the hydrogen economy. Thank you so much for your time.
All right. Thank you for that. I'm just reacting to the TA slide. Can you kind of take me through a little bit of the key assumptions to kind of make the numbers work, especially the H2 release? Or just
man, can I ever? Julian, do you want to take this one?
Sure, I'm happy to. The reason why our system is able to reduce the cost is that we significantly simplify the downstream separation. and improve the efficiency with which we convert the ammonia to hydrogen and then recover it at high purities.
Sorry, does that answer your question? Essentially, we recover a higher percentage of the hydrogen, and it's electrified, leading to some lower costs.
Yeah, I had a question on the uses. So, some great uses shown here. I'm curious why like forklifts is not included in the list, if that was considered as well. And then additionally for like the premium and willingness to pay by end customers, how have you guys been assessing that?
Yeah, no, great question. Forklifts, I didn't realize I had a laser pointer this whole time. I didn't have to walk around so much. Forklifts is that last one. I call it off-road machinery because there are other things that apply there. But forklifts is, for instance, one of the areas where you do see people willing to pay $6 a kilogram for hydrogen in some of these warehouses. The willingness to pay numbers for some of these other sectors, a lot of it is in Europe because, as has been noted by other presenters, America is not the most forward in decarb right now, but these numbers are from what is actually being paid right now. So iron and steel, that's the premium that H2 Green Steel is getting from premium automakers for some of their offtake. Refining, BP and Shell are paying $6 to $7 a kilogram for green hydrogen in some of their refining operations in Europe. Kind of continue going on. Maritime is because of regulations and proposals by the International Maritime Organization. So this is based on actual demonstrated willingness to pay, which is why these are our beachheads.
And sorry, just to confirm that none of these numbers assume the IRA credits for green hydrogen, or do they?
Correct. They do not.
Can you take me a little bit through the journey from like pilot and then scaling this? Like, just how are you thinking about it? Some of the key barriers and challenges you're trying to solve for?
Yeah. So, you know, over my career, I've done a lot of work in electrochemical technology development. And, you know, we've gotten this far largely because there have been a lot of advances in the laboratory first. In order to scale any electrochemical technology, you need to get to some threshold limiting current density values that allow you to really be able to get high enough reduction in CapEx. We're almost there. Even in the laboratory within probably a factor of 2. And that's quite impressive given the conditions we've been working under for just the last year or so on this project. So it's getting to high enough current density, getting to modular stack, getting to large area stack size, getting to uniformity in stack dimensions, getting to effective sealing, other things like that, balance of plant. Those are kind of all the sequence of events that need to happen. But right now we're at the laboratory scale on the sort of centimeter scale level, centimeter by centimeter scale. You know, we'd like to ultimately get to things on the order of meter by meter scale stack plates. And that's the development cycle that kind of has to happen to get to levels that are actually pilot level and ultimately industrially commercializable.
Maybe to echo the last question, what are your funding needs to execute on that roadmap?
Yes. Thank you for asking. Makes me feel better about sticking that in the appendix. So this is some modeling that we've done in terms of what the funding needs would be to get to first kind of a pilot deployment around 100 kilograms of hydrogen per day, and then what we would expect a first commercial deployment size to be. To get to the pilot deployment, we would expect to have to fundraise around $9 million. $3 million of that would be the direct cost of kind of building that first of a kind pilot that we could take around to customers. The rest are lab costs, personnel costs, things of that nature. Does that answer your question? I'm happy to go into more detail on this.
No, that answers the quantitative aspect of the question. And would that be essentially equity or a mix of equity and project financing? How do you think about that?
It's a very good question. Some, particularly for personnel and lab costs, would be equity financing. For the actual CapEx of deployment, I think, sorry, I don't know if the mic, can everyone hear me okay? For the actual CapEx of deployment, ideally there would be some sort of cost share with the industrial facility where we are establishing this, where there's a whole bunch of different models that we could go after, particularly once we've proven out performance and are getting to our first commercial deployment, where they take on some of the balance of plant costs, things of that nature, and we are more of the technology provider. My best guess is for the pilot deployment, a lot of that funding will come directly from us. If there's government grant funding or other sorts of non-VC capital that we can put towards that, that would be ideal. But the baseline expectation is that would come out of equity financing. I know you guys have more questions. Feel free, toss them out there.
Yeah, no, you've answered it in this slide, so I'm good with it. It's just around the scalability of the solution and like the actual volume.
I guess one question on the membrane itself, right? That seems like quite a core part of this whole puzzle. I mean, you said you're kind of operating on what, a centimeter kind of scale at the moment. I'm just curious I mean, obviously everyone knows the price of palladium, the challenges associated with that. I mean, some supply chain considerations. I'm wondering how you think about that from both the technical point of view in terms of scaling it and then the impacts on the economics.
Yeah, maybe I can explain a little bit more about the actual nature of it, right? So we can use a palladium or a palladium alloy-based membrane. So there's ways to thrift the amount of palladium, and there are also ways to actually make multi-layer stacks that take a base metal in between and combine 2 palladium layers on top. So there are ways to thrift the palladium to a very low level, and we're doing some laboratory work to kind of assess the feasibility of how much that is and the long-term durability of that. So there is definitely a development component of this that is on how you thrift the palladium to the lowest possible level. But our techno-economic model kind of takes pretty conservative estimates of that into account right now. So that's kind of the short answer. But then the long-term kind of supply chain answer is, I think that's a bit of an open question, but I actually think that the palladium market will be a little bit more less constrained than we might think in the future, because there are actually sources of palladium that will come online as we, for example, decarbonize a lot more of the automobile market. Palladium that was previously used in catalytic converters and things may actually provide more supply. And if you talk to industry experts in that area, they actually don't see palladium limitation as a primary impediment to using it. And that's why actually palladium members are being thought about in industrial gas separations, actually. So
thank you guys very much.
Thank you. And last but not least, we have Forma.
Hi, everyone. We're Forma Systems. We optimize concrete floors to save cost and carbon emissions. Our team is comprised of the 3 of us. I'm Kylie Fikert. This is Sandy Kurth and Eduardo Gascon Alvarez. Sandy has expertise in 3D printing, low cost and low carbon building materials with a background in mechanical engineering. Eduardo has a background in architecture and structural engineering and has expertise in multi-physics simulation. And I'm also a registered architect, and I have 7 years of experience in practice, most recently working on Google's headquarters in California and London. And the problem that we address is that as much as 70% of construction material in typical building products, including floors, foundations, and walls, is structurally unnecessary. And so this leads to excessive costs and also contributes really significantly to climate change. And so what we do at Forma is we optimize the shape of these building products to safely remove material where it's not required. And so this saves costs, but also drastically reduces the emissions. Our initial target is concrete floor systems, both because they have a large potential for savings, and it's also one of the world's most common building products. So what we actually do is we adapt the geometry of the floors to follow the force demands. So here you can see a typical building usually has flat concrete floors. What we do is we shape these floors to remove the material where it's not required, which allows us to use up to 72% less cement and up to 67% less steel than typical floors. And this material savings results in dramatic cost savings of around 35%. And our slabs are designed to be code compliant, which means that they meet current building codes. They also have reduced weight for transportation and installation, and they result in reduced structural loading on downstream elements, for example, the beams, the columns, and the foundations. And it also allows us to build larger components for faster installation. And in terms of climate impact, in a full deployment scenario, we're able to abate 1.86 gigatons of carbon Just to give you a sense of scale, this is about 2 times the scale of the whole aviation industry. And that's from both savings in the floors themselves, but also the downstream savings I mentioned in other building elements.
And so our main market advantage lies in 2 key technologies we have developed at Forma that are the result of more than 10 years of research at MIT from ourselves and our scientific advisors. The first being an optimization software that really enables to find these highly efficient and optimized concrete structures. And then on the fabrication side, we've also developed a 3D printed mold fabrication technology precisely to enable the fabrication of these components at scale and in a cost-effective way. And so just to walk you through quickly how the software works, we input the building code, the material properties, and the fabrication constraints of a specific context. And we input that into our optimization software, which in a matter of seconds does a task that would typically take hours, if not days, kind of merging 3D modeling with structural optimization and optimizing the shape of a concrete structure for a specific performance metric, such as lowering weight, cost, or embodied carbon. We do this while meeting building code, and then this design is sent to a manufacturing company that is in charge of manufacturing the product at scale. And you might be asking why we don't see, why buildings are not shaped like we're saying if there's so many benefits. And a main reason is that fabricating the formwork, the mold, the kind of the place where the concrete is casted, it's very expensive, especially for more complex geometries. So a key technology we've also developed at MIT and is part of our IP at Forma is a 3D printed mold fabrication technology through low carbon materials that are also recyclable. So we're finding ways to, in a very cost-effective way, deploy highly efficient concrete structures that we're saying they use half as much material. So we have the geometry and we also have the way to make them. And so we've deployed, more importantly, we've deployed this technology at scale already with multiple full scale with prototypes and structural loading, both here in India and Mexico, but saving 50% of material while meeting building code. And we are following a business model that is very conventional and common in the construction industry, but based on a licensing model where we are licensing our shape optimization and mold fabrication technology to manufacturing companies who are then in charge of commercializing their product to the end customer, a home builder or a contractor. Through this process, we have 2 revenue streams. One is a fixed rate fee for the kind of this initial engineering and mold fabrication process, and then a second fee, which is a royalty-based fee for the based on the selling of the product to the end customer. We're very excited. We've already deployed this business model with our first paying customer in Mexico, where we are saving with our optimization software, already saving 16% of material, which is translating today on a savings of 3.5 kilograms of CO2 per square meter. And now we're currently focusing on the US precast market as our beachhead market currently, where we are, first of all, is a large market with up to more than almost 3,000 companies evenly spread out across the country with a big scaling potential. And we're also starting to see traction in terms of from a first partner for our first demonstrator project here in the US. And in terms of timeline and milestones, building on of our progress to date, we are expecting to fine-tune our mold fabrication technology at an industry level in the US with the plan of certifying our product in 2026 and start in the long term with the idea of having our own mold fabrication facility. And in terms of milestones, business milestones, we are planning to secure up to 3 US-based clients for our Forma T slabs, and then in 2026 start commercializing them and licensing our products through our manufacturing clients. So thank you everyone for coming here. We're very excited to be here in the Climate Energy Prize. With this opportunity, we're hoping to use this opportunity to build our demonstrator project here in the US, also expand our customer discovery efforts today, and grow our team as we are developing our business development and fundraising efforts. Thank you everyone for listening.
Thank you.
We are Forma, and yeah, let's make the next question.
So let's say I'm a builder. I would love to, if you could take me through, how does that change my build process? Like, how does that change the actual project management and planning and building of a structure, whether it's a building, a tower, whatever it may be?
Bottom line, it doesn't.
That's what's so great about this innovation. So our very first project, which I have a piece of here, which we conducted a couple of years ago in Mexico, the best part was we weren't there. So we sent the code that was needed, the fabrication instructions, to local manufacturers who are conventional builders, essentially, local experts. They deployed the prototype system for us. We showed up, took some fun pictures with it. And then from that prototype, a local manufacturer, our first client, came to us and said, hey, we want to implement this at scale. We would make a lot of money off of it. They weren't really, particularly interested in the climate aspect. They just saw significant material savings means we make more money. And lighter buildings mean cheaper construction for the developers and, all the way down the line. So that's kind of the whole point. We're using some very high-tech software tools to enable some much better but rather conventional construction.
And just a question, like if you want to expand this globally, so are you like developing the molds in localized facilities and shipping them to the sites themselves, or are you guys thinking of a more decentralized model?
This is kind of why we have this staged approach in our timeline there. Our first client, we didn't need to do anything. We basically gave them an updated design, and it cost them less than $10,000 to retool part of their system to achieve that 16% savings. And a few hours of downtime to swap out that part. For context, the kind of factory that we did this in is the kind of thing that costs $100 or $200 million. So $10,000 to get 16% savings is frankly crazy. So if we want to reach the 50% savings, then yes, we probably need to provide some slightly more advanced tooling, and especially here in the US, where we're trying to deploy much larger precast beams, like things that would span this room. We need to collaborate closely to develop some tweaks to the way the molds are made. And what's so exciting about our sort of current IP portfolio is it allows us to de-risk this innovation for the clients. So normally you want to create a new kind of 12-meter concrete beam. It costs you hundreds of thousands of dollars to make a new kind of production system for that, to even make a prototype to test. Whereas in our case, we can literally use materials that are 10 cents a kilogram to prototype a mold, cast a beam, load test it, get it certified, and then they can say, oh yeah, okay, now we're ready to spend the money, implement this, have a market advantage, and so on.
On your market slide, I think you had 20, 35, and 46 million in terms of revenue. Just curious if you can talk me through that number. I mean, not to be the VC and be like, give a big number, but more importantly, how does that relate to your kind of capital intensity that you'll need over the next 10 years?
Right. So we're mixing here the addressable market in the US and then the targeted revenue for 2035. It's based on a financial modeling we did of these two revenue streams I was talking about, the selling the molds and also a licensing fee based on a expectation of how many slabs we're going to sell in the next 10 years. And this is assuming a 10% penetration depth in the US. So that's where the 46 million number comes from, which in terms of capital for us, of course, right now it's mostly our time. We have the robotic kind of facilities to print the molds. It's actually the material supply, which is also pretty low. So we're running very low on capital costs, and that's also why we're looking for this licensing modeling as a way of kind of ramping up our production capabilities as we secure more clients.
Can you break that down a little bit more for me? So that 46 million, about how many projects is that then that you have in that 10-year horizon?
That's assuming that we are working with 100 companies, but in 10 years from now at the same time, where we're selling molds to each of those, and they are, we're licensing their products to them, and they're selling shaped, optimized beams.
For a little context, the way this works in the construction industry is you have localized production, even in the US, because all the materials are so heavy. So every 200 miles, basically, anywhere in the world, you have some kind of concrete manufacturer who would make these components. And they're often working together in kind of consortiums where they agree on designs. So we've been in quite a few conversations with the local, basically precast cement organization to get our design to be like one of their go-to precast options. And once you do that, then you're kind of in this pipeline. Like once you become a standard product, you can be anywhere very quickly.
Maybe sort of building off of that, how do you guys think about who you need to bring on from the team perspective? Maybe in the near and midterm, not necessarily in that full 10-year vision, but who else do you sort of need to bolster the team with to continue to push forward?
Yeah, well, I'm excited to announce that Adib has joined our team recently to help us with business development because, as you can probably see, we have a lot of technical and construction expertise. We don't have a lot of business expertise, so we're very excited to have him join the team. But I think also looking to bring others on with more business background and fundraising background to help us scale.
Maybe a quick word on the competitive landscape that you're facing.
Yes.
Do you want me to take it? So there are only a couple of other companies who are looking at optimizing concrete systems. Holdeck is an example, Ripman Floor System. We're achieving about the same carbon and material savings as them. One thing is that they often use plastic injection molded parts to create voids within floors. And so their carbon footprint is usually much higher than ours, but they are already operating at scale. And so we're in a process of trying to get the fabrication speed down, the installation speed down, because that will make us cost competitive with some of these existing systems, but also achieve better carbon savings than folks who are using plastic as their molding.
Can I add something? Another kind of quick advantage. I think we're one of the few, the only company that kind of merging design optimization with fabrication, and that gives us like a huge flexibility in terms of how we react, not only to standardized products, but more like bespoke projects, which are also very common in the industry. So that's a pretty unique advantage we have too. Yeah. Yeah. Thank you, everyone.
Thank you.
All right, so that's it for today. What are people's thoughts? How were the startups? Amazing. So now we'll have a 45-minute coffee break and networking break. So get to ask any last-minute questions that you have to the startups, get their contacts, make some new friends. And then after that, we'll come back for the closing remarks and the deliberation of results to announce who's the winner of a $5,000 check and who are the 5 startups that advanced to the final. Thank you.
I just get exposed. Thank you.
One more thing I forgot to say. We have a QR code where everyone can give some feedback to the startups. We know we have a lot of talent here in the room. So if you guys would like to write something for any of the startups, feel free to do so via the QR code. Thank you very much. Hi, everyone. Welcome back to the competition. First of all, I just wanted to really thank everyone who's come here today to support the startups that have been pitching. Also our sponsors, our judges, mentors, partners, the organizing team. Really, thank you very much for making the semifinal of the 2025 Climate Energy Prize possible. To our wonderful startups, thank you for coming. Thank you for all the work that you're doing. And we hope that, regardless of what comes next through the announcement, that you've all learned and grow throughout this process. The community around you is really what we think is going to propel you forward. We have multiple stories of people getting their first check, or a customer or an employee or something from the people in this audience. So definitely happy for that. So before I announce the winners, I do want to kind of highlight some of the things that we've seen today. So, we've seen that we can store energy in the future in our cars or in concrete, or manufacture concrete precast with a fraction of the resources that we need currently. We've seen how we can leverage AI to accelerate carbon storage, how to shrink a nuclear reactor to the size of this podium, which I think is remarkable, transform plastics using electrolysis, decarbonize ethylene, or capture CO2 from industrial processes. We've seen how to solve for the bottleneck in hydrogen transportation, and of course, how to bake pizza with GPUs, or better, how to help chips beat the heat. So please, a round of applause for our wonderful startups here. Great. And now for the great moment, we'll announce in the screen the 5 startups that will advance to the final. And now the winner of the $5,000 check of the US semifinal is Forma Systems. So please join us on stage. We'll take a few pictures, first with the team, and then we'll invite our sponsors to take a picture as well with the team.
Thank you so much. You have stuff on that.
And now we'll have one representative for our sponsors if they want to come take a picture. I think Mitsubishi, and from Mintz, I don't know if we have sauce coming. Perfect. Thank you. Sorry. All right. Well, thank you all for coming here today. Really appreciate it. And yeah, we'll see you all hopefully at the finals as well in about a month.
Thank you.